Hello and welcome to the Mastering TypeScript video course by Pact Publishing. My name is David Sherritt, and I'm going to go along with you on this course. A bit about me. My main work is in the healthcare industry, writing software for specialty pharmaceuticals. In that, there's a lot I do, from writing software to manage the logistics behind those drugs, to creating statistics on patients, to writing software to cut down on health insurance fraud. I've been programming for almost 15 years now, and you can mostly find me answering questions on the TypeScript tag on Stack Overflow. This is an advanced course on the TypeScript language. It's intended for developers who already have a basic grasp of the language and want to attain a deeper understanding of it. In this video, we're going to give an overview of the course. We'll talk about its structure, prerequisites, and goals. In the first section that we're currently in, we'll briefly take a look at the sample application we're going to work with for the rest of the course. In section 2, we'll start diving into the details about TypeScript's type system. We'll look at considerations we had when first writing the code in TypeScript, and look at tools we can use to improve the TypeScript code we write. In section 3, we'll talk about moving some ES5 JavaScript code to ES6 classes in TypeScript, as well as some details and tips on using classes. In section 4, we'll look at ways of interacting with TypeScript's type system. In section 5, we'll discuss representing JavaScript libraries in TypeScript. Specifically, it will be a section on TypeScript definition files, and we'll also look at how we can easily manage definition files in the applications we write. In section 6, we'll talk about some TypeScript language features we can take advantage of to write better code. In section 7, we'll look at some advanced ES6 and ES7 features like generators, async and await, and decorators. Finally, in section 8, we'll talk about ways we can create static typing between a client and server in a client-server application, and at a way we can write our view code with static typing. So from this overview, you can see it's not a beginner course. It's expected you already have a basic understanding of concepts from TypeScript, such as types, interfaces, classes, inheritance, and generics. It's also expected that you have a basic understanding of JavaScript. I'll explain the lesser-known parts of the language, but I won't explain a lot of the basics. However, if there's something you don't understand, you will always be able to pause the video and research the part you're unfamiliar with online. Additionally, it's nice to have a basic understanding of Node.js, Node Package Manager, and Bower, but it's not necessary. You'll get through the course fine if you're not familiar with them. Overall, the main goal of this course is not just that you develop a better understanding of TypeScript, but that you come away writing better TypeScript code using newer features of the language. Come with me as we move towards understanding more of the TypeScript language in this video course on Mastering TypeScript. Hello and welcome to Section 1 of Mastering TypeScript. In this course, we're going to use a sample application that will help us explore different aspects of the TypeScript language. We'll introduce it in this section by doing an overview of the sample application, then look at how we can build and compile the sample application. Now we begin the first video, which is a quick overview of the sample application. In this video, we're going to do a walkthrough of the sample application, and then discuss what technologies it uses. We won't explore the TypeScript language features used in the sample application, but we'll explore that in detail throughout the rest of the course. This is the Slice It Pizza sample application. Slice It Pizza is a very simple pizza delivery service with very simple business requirements. Within this application, we have two main sections, which are orders and food items. Food items are anything you can order off the menu. For example, here we have pepperoni pizza, cheese pizza, and even stromboli. On this page we can add food items, edit, or delete them. You can see when going to edit a food item that we can change its name, adjust the price, or change its status from active to inactive. Then on the orders page, we can add orders, edit, or delete them. An order consists of the name of the person who made the order, their address, the food items they purchased, and the order details, such as the date the order was received, the total cost, the order status, and its priority. When we open up this order to edit, you can see we can edit the details of this order, and add or remove food items from the order. Finally, we have a very simple About page that overviews the details we just went over. So you can see this is a very simple application. There's no login page and there's no user management. So how is this application structured? Well, we have the web app and server app. The web app deals with getting information from the server, displaying information to the user, and handling user interaction. The server app, on the other hand, handles queries from the web app to either put data in or get data out of the database. The server app is completely separate from the web app, and the reason for this is to demonstrate a simple client-server application. The web app uses several technologies, but it isn't necessary to know anything about these to take the course. We'll barely even talk about them. The React JavaScript library and Flux application architecture are used for displaying information on the screen. However, this course won't focus on these technologies. They'll only be in one video in Section 8 that discusses TSX files. The web app uses the less CSS preprocessor, Mocha for unit tests, and Gulp to build the application. This is the last video that will talk about less and Mocha. However, we'll continually use Gulp throughout this course to build the application, and so a basic understanding of how Gulp tasks work is nice to have, but not required. Now looking at the server app, it minimally uses Express to receive and respond to requests from the web app, and uses AnyDB for the database. AnyDB is a lightweight, simple library for storing information in a file. It's perfect for the course because it doesn't require any setup. However, I wouldn't recommend it for a massive application that has many concurrent connections. Again, we're barely even going to discuss these technologies in this course, as we'll be focusing on the TypeScript language, so it's okay if you're not familiar with any of these technologies. Finally, the server app uses Mocha for unit tests and Gulp for the build script. Overall, this application is a very simple setup that will allow us to explore a lot of aspects of the TypeScript language. In this video, we looked at how the Slice It Pizza sample application works. In the next video, we're going to look at what's been decided for compiling TypeScript in the Slice It Pizza sample application. In the previous video, we had a quick overview of the Slice It Pizza application. From here, we will learn how TypeScript code will be compiled in the application. In this video, we're going to quickly review some of the common methods used for compiling TypeScript code to JavaScript. Then we'll look at how TypeScript is being compiled in our application. Now to review. Compilation from TypeScript to JavaScript is handled by the TypeScript compiler, that is, TSC. The code can be compiled by calling the compiler in three common ways. First, by manually calling the compiler from the command line. Second, by letting our development environment's TypeScript plugin call the compiler for us. Or third, by using a build script to call the compiler. For our application, we're going to use a build script. Let's look at some of the reasons why. First of all, there's a lot more flexibility with the build script. It's easier to set up steps for our build that go beyond simply compiling the TypeScript code. For example, we could set up steps to compile, minify, and package our code, or do something else based on different conditions. Secondly, a build script gives us independence from a development environment's TypeScript plugin or an IDE-specific build environment. This means that developers working on the same project can build the application regardless of the development environment they are using. This is especially useful in open source projects. Lastly, a build script makes it easy for every developer to compile the code correctly because the build script will handle the steps for them. Some disadvantages with the build script are that it can be a bit more complex and requires more setup time. However, the advantages for a build script far outweigh the disadvantages. There are many ways to create a build script, but as discussed in the previous video, we are using the build tool Gulp. How to configure Gulp is beyond the scope of this course, and so it has been configured for you in gulpfile.js. The important point to note is that our TypeScript compiler options are stored here in tsconfig.json, but the actual build destination of these files is handled by gulpfile.js. In the future, we're going to look at additional compiler options. But for now, we're going to leave this as is. Before we can run the build script, we have to make sure we have all the dependencies of our application installed. First, make sure you have Node.js installed. You can check if it is by running node-v. I've already set it up here, but if you need to install it, then you can download it from nodejs.org. Now that Node.js is installed, the other dependencies can be installed by running the command npm install from the command line in the root directory of both the web app and server app. You are already probably familiar with this command, but if you aren't, it will install all the packages listed in package.json that are dependencies of our two applications. Understanding this isn't necessary for this course though. Now we're ready to build our application. We can build our server app and web app by running the gulp command from the command line in each of the app's root directory. Now that we have built both our applications, let's run them. To do that, we just have to run the command npm start. In the case of the server app, it will start running the server. With the web app, it will run a local web server and then open a web browser that navigates to that local web server. When doing this, make sure to first start the server app, then start the web app. That way the web app will have something to communicate with when it loads. In this section, we did an overview of the sample application and looked at how the sample application is being compiled. In the next section, we're going to start using TypeScript and discuss more advanced topics relating to the type system. Hello and welcome to the second section of Mastering TypeScript, Deploying the Type System. In the previous section, we introduced the sample application. Our first video will be on when to use implicit or explicit types. Second video on avoiding the any type. Third on being aware of how TypeScript uses structural typing. Fourth on some common troubles with the type system. Fifth at some compiler options for added support, so how we can make the compiler stricter. And finally a video on enforcing rules and coding standards with an external tool. While writing the sample application, some decisions had to be made about when to explicitly define a type. In this video, we're going to look at how we can decide between implicit or explicit types. First, we'll make sure we understand what we mean by implicit and explicit types. Second, we'll look at the case for using implicit types when able. And finally, when we should be explicit instead of implicit. As you should be aware, TypeScript adds optional static typing to JavaScript. This allows us to use types. For example, we could define a variable as a string, and then we wouldn't be able to assign incompatible types to it, like a date. This helps prevent us from making mistakes in our code. Let's look at implicit types. But what do I mean by that? Here we have a variable that is assigned a string. This variable is of type string because the type has been inferred by the compiler using the type of what was initially assigned to it. We can verify that it's been implicitly typed as a string by hovering our mouse over the variable name in most development environments. Now what do I mean by explicit type? An explicit type is any type that is not inferred, like this variable here, but is explicitly defined like this variable. Here, the type of string is not inferred by the assignment, but is defined when the variable is created. When choosing between an implicit or an explicit type, we should try to find a way to maximize the following goals. 1. Prevent mistakes by restricting the range of possibilities that we can write in our code, thereby protecting the programmer from themselves. 2. Write brief and clearly expressed code. Let's take a look at how we can do that. First, let's look at an example with a variable, and I'm going to type this out as we go through this. Our variables should be defined and assigned to in such a way that the variable name and assignment express the type on their own. When looking at this statement, we can see the type of this variable is a date by looking at what is assigned to it. and its name helps. Explicitly defining our variable in this case doesn't help us. We now have duplicate information in our code, and when we want to change the type, we have to change an additional place. Similarly here, if we assign the result of toShortDateString to a variable shortDateString, we can tell the type by the name of the variable and by the right-hand side of the expression. Had we not used descriptive names, say name this D, and this method convert, it would be much more difficult for us to figure out what the type of this variable is. This is why it's crucial when using implicit types that we also use descriptive names. Now, when should we be explicit? Here are some good rules to follow. 1. Be explicit when the type will be implicitly typed to any. And 2. Be explicit when assigning to a parent type. Otherwise, write descriptive code to eliminate the need to be explicit when the type could be implicit. Let's look at these two cases. Here in number helper, there's a parseString method that takes a string parameter and returns it as a number if the string is able to be parsed as a number. Otherwise, it returns undefined. I've expanded out the body of the method for the sake of this example. Within the method, we have a num variable that is implicitly typed to any, which means the num variable could be assigned a value of any type. It is being implicitly typed as any because no expression is being assigned to it whose type can be inferred, and no type is explicitly defined. But why could not being explicit in situations like this lead to problems? Well, say we accidentally assigned a string to this num variable. Since the variable is implicitly typed as any, it doesn't prevent us from doing this, and it doesn't notify us of this mistake with the compiler. Now we will have to run our unit tests before we get notified there is a mistake, then spend time trying to figure out why our test failed. It would be even worse if we didn't have unit tests, as we would have to spend even more time before finding out it was a mistake. And sometimes we might not even notice a mistake until someone else points it out. Additionally, this method's return type is typed as any because it infers the return type from the returned values type, which is the any type. This could lead to further problems for code that uses this parseString method. Not explicitly defining our variables can result in wasted time and bugs. We can eliminate this problem completely from our code by explicitly typing our variables and avoiding the any type. For now, we know it's advisable not to do this, but in a future video in this section, we'll look at how we can force ourselves to never make this mistake. In addition to this first case, we also should be explicit when we want to type a variable as a parent type of the value being assigned to it. For example, with this code, the type on the right-hand side of the assignment is the child type, but we explicitly define this variable as the base type so that the child type is not used. In the end, it's important to find what works for you and your team. Develop a standard and stick to it. The information in this video should help you do that. In this video, we looked at implicit and explicit types, as well as when we should use one over the other. In the next video, we'll look more in depth at why we should avoid the any type. In the previous video, we looked at using implicit and explicit types. In this video, we're going to take a look at avoiding the any type. We'll look at why we should do that, and then at some language features we can use to help avoid it. So first of all, what is the any type? The any type is essentially a way to opt out of type checking. It allows us to use a value in any way that is syntactically correct. So why should we avoid it? Using the any type opens us up to all kinds of problems that we used to experience before switching from JavaScript to TypeScript. We lose static type checking and the ability to refactor our code. Here we have a variable, food item storage, which we can use for getting food items out of the database. Right now it's typed as the food item storage class, but if we explicitly type this as any, the compiler will let us use the variable in any way we like. We could write food item storage.myNonExistent function And we won't get a compile error, but we will surely get a runtime error saying that this function doesn't exist. Essentially, by using the any type, we have lost our friend the compiler, who helps keep us in check. To avoid the any type, values should be described with types. But what happens if we have to have a value that could be one or more types? What do we do then? TypeScript has a language feature called a union type. A union type allows us to say a value could be one of several types. Here in Number Helper, there's a very simple method called format_as_currency. For the sake of this example, I've changed the code found in the sample application because it contains concepts we'll talk about in a future video. In this example, format_as_currency takes a number and returns that number formatted as a currency string. Say we wanted to make this also accept a string instead of just a number. We would add a vertical bar and then write string. Now this parameter could possibly be a string or a number. Since we did this, we now get an error on toFixed, because it's a method that exists on number, but not on string types. We need to change our function to work with this. We can do that by using a type guard to check the type of val before using it. Essentially, a type guard allows us to separate out the types from a union type. It works by using an if statement to check if the variable is one of the types, and then the variable will be that type within the if statement without any additional effort. If we check if val is a number here, the type of val will be a number within this if statement, and our compile error goes away. We can finish up by adding an else condition where val will be typed to a string within. Now we have changed our function to fully conform to the possible types it expects. In this video, we looked at why we should avoid the any type. We also saw a way of avoiding it by using union types. Overall, sometimes using the any type can't be avoided, and in certain scenarios it makes sense. But when you can, I would encourage you to avoid using it, or at least limit its exposure in your application. In the next video, we'll look at the specific type system TypeScript uses for determining the compatibility and equivalence of types. In the previous video, we looked at avoiding the any type. In this video, we're going to take a look at the specific type system TypeScript uses for determining the compatibility and equivalence of types. First, we'll do a bit of an overview of the type system, then examine its benefits and dangers. So how does type compatibility and equivalence work in TypeScript? Here we have a function that accepts an interface called myInterface. I've created a class, myClass, that implements this interface. You can see here that we can pass myClass into the function no problem. Keeping in mind that this function has the first parameter enforcing the type myInterface, what happens if I remove the code that says the class implements the myInterface? Nothing. There's no compile error. Well, how can that be? This might not be what you expect if you are more familiar with type systems in programming languages like Objective-C, C++, C#, or even Java. Well, the reason for this is because TypeScript uses structural typing. So what is structural typing? Structural typing, otherwise known as property-based typing, is when the properties of the type are used for type compatibility and equivalence, rather than the name of the type, as would be done in a nominal type system like C# or Java. So again, a structural type system, like in TypeScript, uses the properties, while a nominal type system uses the name of the type or the name of a subtype. So how does this benefit us? Taking a look at our previous example, TypeScript allows us to pass in an object that isn't explicitly defined as myInterface. If we pass in an empty object, we will get an error because it doesn't match the interface. But once we add the required properties, that error will go away. Note that as of TypeScript 1.6, the compiler is stricter in that it doesn't allow us to have additional properties on the object we pass in. If we want to tell the compiler that we mean to do this, we can tell it that by doing a type assertion. The obvious danger with structural typing is that we might equate two types that would lead to a bug in our code. This bug can usually be caught in our unit tests, though. Another downside to structural typing is that it makes it difficult to use certain design patterns that work well in nominal type systems. for example tiny types. In this video, we looked at how TypeScript uses structural typing. In the next video, we're going to look at a few examples of some problems we can run into with the type system. In the previous video, we looked at how TypeScript uses structural typing. In this video, we're going to take a look at a few common troubles with the type system. First, we'll look at an area where the language design might cause some trouble. Then we'll look at a case of changed behavior where a compile error is no longer thrown. Then, we'll move on to where the compiler has not implemented certain aspects of the type system. And finally, add an instance of a language feature that might not be for our best benefit. Let's look at one area where an aspect of the language design can cause some trouble, and it's with the enum type. We're going to describe enum types in depth in a future video, but for now, one quick note to say about them is that an enum represents a set of constant numbers in a readable way. Here we have our order priority enum. It allows us to represent these values of low, medium, and high with a corresponding number. For example, order priority.low represents the number 0. What you need to be aware about with enum types is that they are a subtype of the number type, and so it is completely valid TypeScript to assign any number to an enum type. For example, in our file here, I could declare a variable that is typed as order priority. Then I could assign the number 50 to it, even though 50 is not anywhere in the order priority enum. This is dangerous, because it gives us the possibility to assign a value we might not expect to an enum type. There are also some aspects of the type system that have changed. In previous versions of TypeScript, you could constrain the type of all the object's keys. This could be done similarly to as shown here, where a number is set for the key type. Now when assigning to settings 4, you can see it expects a string value. However, the changed behavior is that we can now write something with a string key, and the compiler won't complain regardless of the key type being specified as a number. We'll actually solve this problem in our next video. There are also certain aspects of the TypeScript language that haven't been implemented by the compiler for complexity or performance reasons. For an example, I've created some dummy code here that shows an array that contains an object with a string ID property being mapped into a function that gets the ID. The only problem is that this function expects objects with an ID property that's a number and returns this number. As you can see, our array has been implicitly typed as a number array, but no error has been thrown about this ID being a string, even though this function expects an object with a number ID property. According to the TypeScript compiler team, the reason it does this is for performance reasons, but they might revisit implementing this in a future version of TypeScript. Finally, when using TypeScript's language features, you should never sacrifice readability for the sake of using a language feature. For example, in most situations, unless absolutely necessary, I would recommend avoiding the tuple type. The tuple type makes it more difficult to understand what's going on in the code by hiding its meaning. For example, to figure out what info tuple 1 is, I have to look at the original definition and assume the string Bob means someone's name. But if I were to have just used an object, it's extremely easy to tell that infoObject.name refers to the name. Overall, it's about picking what works best for the scenario and what works best for you and your team. In this video, we have looked at some troubles we might have with TypeScript's type system. In the next video, we're going to look at some compiler options we can use for more support beyond the existing type system rules. In the previous video, we looked at a few troubles we can run into with the type system. In this video, we're going to take a look at how we can make the compiler stricter. First, we'll look at a compiler option for doing this, and finally at some ways we can get around it. As discussed in previous videos, implicit any types should be avoided, but occasionally as developers we might make a mistake and not notice we created an implicit any type. To fix this, we can use the compiler option called noImplicitAny. This compiler option causes implicit any types to throw a compile error when they're used. For example, With the option enabled, if we create an implicit any type here, don't set the type of this parameter, or even forget to set the type of a property, the compiler will throw an error in all these cases, because implicit any types are no longer allowed. Of course, any types are still allowed, but we just have to be explicit about it and let the compiler know, yes, I really want to do this. This feature brings a huge advantage to development in TypeScript, and I would recommend enabling it by changing the compiler options in tsconfig.json. Here you can see I've already set no implicit any to true. No implicit any actually solves the trouble we had with index types in the last video by now throwing an error, but some people might not want this. Some developers sometimes want to reference a non-typed property using brackets in order to work around the type system, and that might be desirable in certain situations. One way we can work around this is to cast the object to the any type. I recommend this way. The second way is to add the compiler option suppress implicit any index errors, which will allow us to do this without error. Overall though, I would recommend finding ways to avoid encountering this scenario in the first place, and not enable this second compiler option. In this video, we have shown the no implicit any and suppress implicit any index errors compiler options. In the next video, we'll look at enforcing rules and coding standards in a TypeScript application. In the previous video, we looked at using the compiler to help us make the code stricter. In this video, we're going to look at using an external tool to enforce strictness and standardization in our TypeScript code. First, we'll install this tool. Then we'll look at an example of using and configuring it. When writing code, it's helpful to have a third party check up on our work. Sometimes we can forget a project's coding standards, or use the language in a way we really should be avoiding. That's where a linter comes in. A linter forces our code to conform to a predefined set of rules, and then can help us write better TypeScript. You'll see what I mean by this in a bit, but first let's go ahead and install a popular linter for TypeScript called tslint. To install tslint globally, open up a command line and run npm install -g tslint. Now that we have tslint installed, we need a way to tell it what rules we want to enforce. This is done by a configuration file. tslint by default searches for tslint.json. I've already included a configuration file in our sample application. You can find a similar sample configuration file on tslint's GitHub page. Let's look at an example of how we can use this. Here we have datehelper.ts. Datehelper is mostly used to format dates in our project. Before we run this, I'm going to make a few changes to the file. First, I'm going to disobey our coding standard and create 2 blank consecutive lines. Second, I'm going to surround this line of code in an eval function. Now let's run tslint against datehelper.ts using our current configuration. Ideally, it's best to let our build script run our linter, but for now we'll run it manually from the command line. To do this, we run tslint, and then the path to datehelper.ts. As you can see, tslint notices several problems with this file. One problem it has noticed is we are using 2 consecutive blank lines. This is because we have enabled the rule no consecutive blank lines. Let's remove the extra blank line, run tslint again, and now we see that error is gone. We still have a few typedef errors though. tslint notices that our method's return types don't have an explicit type definition. In other words, the configuration currently requires all return types to be explicit. I don't want that because it's my preference to define return types implicitly, so I'm going to disable this by opening tslint.json and setting the first value in the typedef array to false. This configuration is quite a lot to explain, so I would recommend going through tslint's GitHub page and reading the documentation to get a better understanding of what I'm doing here. The important point to note is that I have disabled this rule, as we can see by writing tslint again. The final error is we can't use eval. It is generally not advised to use eval because it can be dangerous, and so I've enabled the no eval rule. We can fix this by reverting this line back to the way it was. Now tslint runs without finding any problems in our code. tslint is highly configurable out of the box, but it also allows us to implement custom rules to meet our needs. I would highly recommend you use it, or a similar linter to enforce the rules you want and your application's coding standards. For more information on tslint, you can visit its GitHub page shown here. In this section, we have looked at TypeScript's type system. First, we had a video on implicit or explicit types, then videos on avoiding the anytype, being aware of structural typing, type system troubles, compiler options for added support, and finally this video on enforcing rules and coding standards with tslint. In the next section, we're going to look at ES6 classes. In this section, we're going to look at how we converted some of the old JavaScript code to ES6 classes in TypeScript, and then look at a few language features that are useful when using ES6 classes. First, we're going to have an introduction on our process before we move to ES6 classes. Then we're going to go through a few examples of some class-like JavaScript patterns in TypeScript. After, we'll look at some static class-like patterns, shortening a class with parameter properties, and finally a video on arrow function properties. Before we begin, here are some topics I would recommend looking into in case you aren't familiar with them. We won't be talking about these topics in this course, but they're extremely useful to know about and can help you write better code. One of the best parts of TypeScript is that it gives us the ability to use future JavaScript features, like classes, now instead of having to wait for runtime environments to support it. We looked at ES6 classes before, but in our initial conversion of the project from JavaScript to TypeScript, how did we convert to ES6 classes? In this video, we're going to start looking into ES6 classes. First, we'll talk about non-ES6 class patterns. Second, we'll discuss what makes a good candidate for an ES6 class. And third, we'll talk about our strategy for moving to ES6 classes. JavaScript is a powerful language, and in the JavaScript world, there's a lot of debate about what patterns should be used. A lot of these patterns are good and have their respective advantages and disadvantages. However, this video and section will not go into most JavaScript patterns, but instead focus on ES6 classes and some JavaScript patterns that transition easily to ES6 classes. The important point to take away is that you can still use these other patterns in TypeScript and still take advantage of TypeScript's type system. For these other patterns, I would recommend doing some research online and finding some solutions that work well for what you are trying to achieve. Now, what is an ES6 class? For the scope of this course, it's already assumed you know the answer to this question, and that you are already familiar with object-oriented design patterns. In this file, we get a quick reminder of what an ES6 class looks like. Similarly to the rest of our application, we are storing one class per file, then exporting it for use in other files. In past versions of JavaScript, before ES6, which by the way is also known as ECMAScript 6 or ECMAScript 2015, no class keyword existed, so class-like structures were often simulated using functions. So what JavaScript code is a good candidate for a class? The best JavaScript code to convert to classes is any code that creates an object of a specific type. For example, this is what the JavaScript code of food item storage looked like before we made it a class. We have a function that creates an object with a specific shape. We'll take a look at this code more in the next video. Overall, we should be using classes as extensively as possible because it helps us organize our code and keeps everything clean and descriptive. When we do come across JavaScript code that doesn't line up with object-oriented design principles, then we should change the design so that it does. So what's our strategy we're going to use for converting our JavaScript class-like code to using ES6 classes in TypeScript? Well, first we'll identify the methods and properties. Second, we'll identify the scope of our methods and properties. For example, if they should be private, public, or protected. Third, we'll convert everything to an ES6 class. And finally, since we're using TypeScript, we'll explicitly set the type information for any implicit anytypes, as required by our coding standard. In this video, we've started to look into ES6 classes. In the next video, we're going to take a look at converting some common JavaScript class-like patterns to ES6 classes in TypeScript. In the previous video, we were given an introduction to moving away from other JavaScript patterns and moving to ES6 classes in TypeScript. In this video, we're going to use what we learned and look at converting some old JavaScript code to use ES6 classes. We're not going to explore all the patterns, but over the next two videos, we'll step through two simple examples and talk about some of the benefits we now have after switching to an ES6 class. Let's open up our server app. In it we have some code as it looked before we switched to an ES6 class in TypeScript. This code specifically is for a class called FoodItemStorage. FoodItemStorage is used to list, insert update, and remove food items from the database. Using our strategy from the previous video, to convert from a JavaScript class-like pattern to an ES6 class in TypeScript, we can identify the methods and properties, then identify the scope of these members, convert it to an ES6 class, and finally type our implicit any types. We're going to focus first on our methods. Here we have three functions: list, insert update, and remove. And they are defined on the FoodItemStorage prototype. Defining these functions on the prototype means that these functions will be shared across all instances of FoodItemStorage. If you're unfamiliar with prototype in JavaScript, I would recommend you stop and do some additional research on it. In this course, it's assumed you're already familiar with it. Now, to determine the scope, for public methods, we can look for functions that are used outside a class. While to find private methods, we should look for functions used exclusively inside the class. List, insert update, and remove will all be public methods in our final ES6 class, because they are all used outside of FoodItemStorage. There are no private functions here, because there aren't any functions defined that are used exclusively inside FoodItemStorage. We'll see an example of a private function in the next video. Let's look for our properties now. There's only one, and it's FoodItemDB. FoodItemDB is passed into our class, and it's what's used to interact with the file that contains the food items. We can use the same principle we used for determining the scope of the properties as we did for determining the scope of the methods. In this case, FoodItemDB is not used outside the class. It's only used inside, and so we know this will be a private property. Let's go ahead and quickly convert this. And while we do this, I'm going to have the ES5 JavaScript output of our TypeScript being shown on the right side of the screen. ES5 is the version of JavaScript before ES6, and it doesn't support the class keyword. First, we'll define our new class using the class keyword, like so. Second, we're going to define our properties. As discussed before, we have one private FoodItemDB property. In this case, I'm going to remove the underscore prefix, because that's not part of our TypeScript coding standard. Third, we'll define the constructor of the class. As you should know, the constructor is the function called when creating a new instance of a class, and in this case, it's almost identical to the original function. Fourth, we're going to define our public methods. Note that the public keyword is not required for defining the scope of a member as public on a class. The decision to use the public keyword or not should be part of your coding standard and enforced by a rule in a linter like tslint. Finally, since our coding standard is to only type implicit any types, I'm going to do just that, but I'll do it quickly because type information is not the topic of this video. You'll notice that when our TypeScript is compiled to ES5 JavaScript, it looks almost identical to our original JavaScript. This is because our original JavaScript code happened to be almost identical to the way an ES6 class is compiled by the TypeScript compiler to JavaScript. We have some advantages though. Our code now looks a lot cleaner, and when we define a method, we don't have to retype out fooditemStorage.prototype each time. Additionally, TypeScript wraps the code in an anonymous function, so that the fooditemStorage function is no longer hoisted beyond this statement. This ensures that at runtime, our class is completely defined with all its methods before it can be used. It's not so helpful in our case, since we are defining one class per file and using external modules, but it can help prevent bugs in certain situations. One disadvantage to this code is we now have type information for fooditemDB in two places. We'll look at fixing this in an upcoming video in this section. In this video, we have looked at one example of a common class-like JavaScript pattern being converted to an ES6 class in TypeScript. In the next video, we're going to look at a second example of this. In the previous video, we looked at one example of switching from a common class-like JavaScript pattern to an ES6 class in TypeScript. In this video, we're going to do the same thing, but look at a second example and examine the benefits gained by switching to an ES6 class in this case. Let's look at this second example. This is Storage Factory, which is used to create objects which can interact with the database. For example, this method creates instances of the class we just looked at in the previous video, that is, fooditemStorage. It handles passing in the necessary configuration to our storage classes and returns instances of them. We have config here, these two functions here, and finally a createWrapper function. These functions are used outside Storage Factory, so we know they'll be public. The difference with this pattern is that they'll be defined on the instance of the object, instead of all the instances sharing a method defined on the function's prototype, like the last example. We also have two private members. Both config and createWrapper don't need to be accessed outside Storage Factory, and so we can define those as private. One point to highlight about this pattern is that it makes it impossible for us to access createWrapper because it is only visible in the scope of this function. Now let's convert this to an ES6 class. We'll create the initial class using the class keyword. Now define our private property. Create our constructor. Change these two functions to be public methods of our class. Define our private method. Fix our references. And finally, I'm going to quickly type the implicit any types on this class again. One additional step I'm going to take is that previously we documented our class's config object in a comment. I'm going to remove this comment because the config object is now described well enough in the type information. Some advantages in this scenario are first that it is again much more readable. Second, that all instances of Storage Factory share these methods on the function's prototype instead of each instance having its own function. And third, it's really easy to use inheritance with our class now. Our last code would have been a bit more difficult to manage. One new disadvantage with this class is the config property and createWrapper method are no longer completely inaccessible from outside the class. This could potentially be an issue if the other code is written in JavaScript, because the programmer will be able to access these undocumented members, since they're now defined on the function's prototype. Generally, to solve this issue, private member names are given the underscore prefix. This is a common JavaScript convention to signify private members. However, just because they are prefixed this way doesn't mean everyone won't use them. Some people might, and that could be an issue. Right now there's no way to completely hide private members in the generated JavaScript, and so switching to ES6 classes in this example is a bit of a trade-off. In our application, it's not a big deal at all because all of our code is using TypeScript, and so using these private members will cause a compile error. In this video, we have looked at a second example of a common class-like JavaScript pattern being converted to an ES6 class in TypeScript. In the next video, we're going to look at some static class-like patterns in TypeScript. In the previous videos, we looked at some class-like JavaScript patterns in TypeScript. In this video, we're going to look at some static class-like patterns in TypeScript. We'll look at two examples of some patterns that work well in ES5 JavaScript, then one TypeScript example, and then discuss what we're doing in this application. Here's an example of a static class-like pattern. This is our main factory. Main factory creates instances of specific classes, such as the class we saw in the last video, that is storage factory. It handles passing in the necessary configuration so that we don't have to think about it when we make new instances of these classes in the application. For example, to create a food item storage, we would do main factory.create storage factory.create food item storage then use food item storage here. Here we create an object called main factory, define some methods on the object, and export it from this file for use in other files. The reason it's a static class is because the methods are available without making new instances of main factory. They're available right on the main factory object. One issue with this way of doing things is that the private members need to be defined outside the main factory object. For example, we could add a private function here or declare a private variable. The important part would be to not export our private members from the file. Let's look at this same class in a different way. Since we're using external modules, we have changed this to instead be a series of functions. The advantage is that we now have more consistent syntax where all our functions are defined in the same way, but we only export the functions we want to make public for use in other files. Here's one final example of another way main factory could be written, and it's using an ES6 class. Compared to a normal class, the difference here is that we create a class as usual, but we only define static members on it, and no instance members. As you can see here in the compiled JavaScript, an empty function is created, and then static methods are added onto the function afterwards. The one issue with this approach is someone can still create a new instance of the class, and there won't be an error. Nothing can be done with the instance though, so to me personally this is a non-issue. Overall, all these methods work well in TypeScript, and there's not a need to use a class. However, the decision made for this application was to use a class with only static members. In your application, the important point is to find a method you like, develop a standard, and then stick with it. In this video, we looked at a few examples of static class-like patterns. In the next video, we're going to look at how we can shorten a class with parameter properties. In the previous video, we looked at some static class-like JavaScript patterns in TypeScript. In this video, we're going to shorten our class with parameter properties. First, we'll look at what parameter properties are, then how to use them, and finally, at what the compiled JavaScript code looks like. For this video, we're going to go back to the storage factory class we saw a few videos ago. In our initial change to an ES6 class, we talked briefly about how one of the problems we had with switching was that we now had type information for config in two places. In addition to what we talked about, we also have to remember to assign our constructor parameter to the property. There's a way we can eliminate these problems though. TypeScript has a neat language feature called parameter properties. Parameter properties are a way to specify that a passed-in constructor parameter should be a property of the class. It shortens the amount of code we have to write, and it makes it easier to change our code in the future. To make a parameter property, we just have to add a modifier before a constructor parameter. In our case, it means adding private before config. Now we can remove our assignment and the parameter defined outside the constructor, because they are no longer necessary. This means that config is now a private property of the class. If we wanted to make it a public property, we could change this to public. if that made sense based on the situation. Let's quickly look at the compiled JavaScript. We can see that by using a parameter property, the compiler does the assignment to the instance for us. In this video, we looked at shortening a class with parameter properties. In the next video, we're going to look at when to use arrow function properties. Hello and welcome to this video on when to use arrow function properties. In the previous video, we looked at shortening a class with parameter properties. In this video, we're going to take a look at arrow function properties. First, we'll discuss what arrow functions are, then we'll talk about using one on a property of a class, or not using one. Understanding the difference between arrow functions and function expressions is vital in ES6, and therefore in TypeScript. Take this example. One of these methods uses a function expression in the body, and the other uses an arrow function. The code is almost identical, but only the arrow function will properly get the my property value from the this reference. The function expression will output undefined because it instead uses window for the value of this. The reason it works this way is because arrow functions lexically bind the value of the this reference so that it is the same value as its parent scope. We can verify that by hovering our mouse over the this reference in both of these examples, and see when using a function expression, it is typed as any. But in the arrow function, it is typed as the class. Let's look at why we might want to define a property on a class, and then assign it an arrow function. With respect to classes, arrow functions are a useful tool for capturing a class's this reference at the point the class is created, instead of when the method is invoked. To demonstrate the difference, I've created this test class with two members. One is a property that is assigned an arrow function. Then we have this method which will be transpiled to a function, which is assigned directly to the prototype. We can see here in the generated JavaScript how each instance of my class is assigned the arrow function property, while the regular method function is defined once on the myClass function's prototype. Additionally, look at how the arrow function property uses the variable that captured the value of this at the time the instance of myClass was created. We can tell that it will always use the instance of the object and not the value of this that could be bound to the function. Let's run this code and then create an instance of this class. If we call arrow function property, we can see it logs the instance of the object as we expect. The same happens for our regular method. Let's call our methods by using the call function that exists on all functions in JavaScript. Call allows us to call the function and supply any value for the value of this, which is specified in the first argument. If we call regular method using call and supply it an empty object, the value of this in the method is the empty object we passed in. However, if we call arrow function property the same way, the value of this in the method is the value of the instance because it preserves the value of this at the time the instance is created. The problem of losing the value of this is common in JavaScript, and it normally happens when someone passes in the method to a different function. For example, say we define a click event on our document and then pass in the regular method function directly. This will be an issue because now the this value in regular method will refer to the document rather than the instance of the class. This can be solved by instead using an arrow function property, as we can see by doing this. However, we can also solve this issue with our regular method by wrapping our regular method in a function and passing in that function to the addEventListener function. Arrow function properties are good because they guarantee the value of the this reference will always be the instance of the class. The only downside seems to be that they don't share functions on the prototype. But is this really such a big deal? Memory is cheap these days, and in most scenarios, we won't be creating thousands of instances of our class, where the user could maybe see the performance benefit. At this point, it might seem like we should always use arrow function properties, but there's one major downside to it that we haven't talked about. It's inheritance. Arrow function properties don't work well with inheritance, because they are a property and not a method. I've created this child class here, and you can see that it's impossible to call the parent class's arrow function property on the super object, but the regular method works fine. So overall, there are some benefits and drawbacks to using an arrow function property, and the decision on when to use one or not really depends on the context. I would encourage you to stick to using methods as much as possible, but occasionally it does make sense to use an arrow function property. In this section, we looked at moving to ES6 classes, looked at static classes, and at a few class-specific features. In the next section, we're going to start looking into interacting with the type system. Hello and welcome to Section 4 of Mastering TypeScript. This section will be on interacting with the type system. In this section, we will look more in depth into type assertion and type guarding, then at multiple function signatures, advanced function use with rest parameters and the spread operator, extending built-in types, and finally code refactoring in TypeScript. Now we move on to the first video of this section, and it's on type assertion and type guarding. In this video, we are going to go through a simple example that demonstrates type assertion and type guarding. We're going to look at some new syntax for type assertion, and then we'll discuss when we should use type assertion and when we should use type guarding. Type assertion is a useful way of telling the compiler exactly what subtype of a type an object is. To fully understand this, let's look at a simple example that often causes some confusion. In this simple example outside our sample app, we have a text box and a button that says Show Alert. Let's make this example work by showing an alert with the text of the text box when we click the button. First, I'm going to wrap our code in a DOM content loaded function to ensure this code won't be executed until the document is completely ready. This is similar to the jQuery ready function and ensures our elements will be accessible once our code runs. Now let's get our elements from the DOM. First, we'll select our text box, and then we'll select our button. Now we have to add a click event onto the button. Let's go ahead and do that. And finally, let's show an alert with the value of the text box. Aha! We finally come across our error. The compiler is telling us that the property value doesn't exist on the type HTML element. The problem here is that the type getElementById returns is an HTML element, but getElementById will return a subtype of HTML element depending on the element it gets. For example, if we select our div element, it will return an HTML div element, and if we select our input element, it will return an HTML input element. The compiler doesn't know what specific subtype the function should return, because it's only provided with a string. So how can we tell the compiler that our variable text input should be an HTML input element and not just an HTML element? Well, we can look at what we used in video 2.2 and use a type guard. To do that, we'd surround this statement in an if statement that checks if the type of the variable is an HTML input element. Our code works now because in order to get to this statement, the HTML element must be an instance of the subtype HTML input element. And so since this is proven to the compiler, it makes this variable the type of the subtype within the scope of this if statement. There's a bit of a problem with this though. Although it works, it was a bit much to write, and since we have the knowledge that text input will always be an HTML input element, this is a needless check. So isn't there a way we can somehow tell the compiler this variable will always be an HTML input element? How about using an explicit type? That might work. Doing that removes the error for text input not having a value property. But now we get a new error. Remember that getElementById returns an HTML element, which is the parent type of HTML input element. In this case, the compiler cannot prove that the type HTML element in the right-hand side of this expression will be an HTML input element, and so it throws an error. We can see by this that we need to tell the compiler that the right-hand side of our expression is an HTML input element, and that's where type assertion comes in. To do that, we just have to add the type surrounded in angle brackets to the beginning of the right-hand side of the statement. Now text input is typed as an HTML input element, and the compiler no longer complains. Although not necessary for our example, let's type our button element as an HTML button element, but we're going to do it slightly differently this time. In this case, we're going to use new recommended syntax introduced in TypeScript 1.6. To use it, add the as keyword to the end of the line, and then put the type you want to assert to. In the case of a button element, it's an HTML button element. This syntax is recommended from now on because it doesn't conflict with similar syntax used in TSX files. Now when should we use type assertion, and when should we use type guarding? A simple rule is to use type assertion when we know the type will be a specific subtype, and use a type guard when we don't know what the type will be. In this video, we have looked at type assertion and a bit more into type guarding. You now also know when to use a type assertion and when to use a type guard. In the next video, we're going to look into using type guarding a bit more by using user-defined type guarding. In the previous video, we looked into type assertion and type guarding. In this video, we're going to look into making the most of type guarding by using user-defined type guards. First, we'll look at an example where standard type guarding doesn't work. Then we'll look at one alternate solution, and then our final solution, which will use user-defined type guarding. In our server app, we're going to look at two interfaces that describe the shape of some of the data we're passing around. One is our food item interface, and the other is our order interface. Food item describes an item currently on the menu in Slice of Pizza. For example, it could be used to represent pizza, fries, and soft drinks. Order describes the order information, such as the person's name and the address of the person who ordered. For this example, I've created a file that imports both these interfaces. Let's look at this problem now. Say we had an object that could possibly be a food item or an order item. How can we tell if the object is a food item? In this case, we can't use instance of, because food item is only an interface that describes how an object will look like. Interfaces won't be in the compiled JavaScript, and so we can't use it in a runtime expression. Additionally, there's no way we can use type of, because it will return object for both food item objects and order objects. The only way we can tell if the object is a food item is by checking to see what the object looks like. The phrase used commonly is that if it looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. This same line of reasoning can be used here to tell if our object is a food item. Looking at our food item interface, we should try to spot out a property or combination of properties that we can use to tell ourselves that an object is a food item. We should be careful to use properties that won't be undefined. In this case, finding a property or some properties to use is quite easy. We can just use the food item ID property. So in our example, we're first going to make sure this object isn't null or undefined, and then check if the object is a food item. To do that, we're going to check if the food item ID property is a string. Now we know that myUnknownObject is a food item inside this if statement, but there's a problem because in the if statement, myUnknownObject is still a union type of food item and order. Since we know that myUnknownObject is going to be a food item inside this if statement, we can assert to the compiler that myUnknownObject is a food item. Now this code will successfully be able to tell if myUnknownObject is a food item, and then a variable typed as food item can be used within this if statement. Even though this works, there's a few problems with this. First of all, we should move this check into a reusable function. Let's go ahead and do that. Ideally, we'd want the isFoodItem function in its own file, so we can easily import it across our application. But we're going to leave it here for the purpose of our example. Note that I had to use an AnyType here, and that's because we want to allow ourselves to check if any kind of object is a food item. But we've used a type assertion here in order to get strong typing with our food item properties. Remember that type assertions are only used at compile time, so this type assertion will disappear in our compiled JavaScript. Now the second problem is we have this type assertion here. To get rid of it, we can use a user-defined type guard. A user-defined type guard allows us to not use a type assertion, and say that if this function returns true, then the variable inside the if statement is of a specific type. In our case, we'd want to tell it that it's a food item. Note that user-defined type guards are only available in TypeScript 1.6 onwards. If you're using a version less than that, you'll have to leave the code with the type assertion. Now to use a user-defined type guard, we can simply specify in the return type that our parameter, that is, object, is a food item. Now that we've done this, if we check the type of myUnknownObject within the if statement, we can see that the compiler has made it a food item because it has sufficient information to prove it's a food item. User-defined type guarding is yet another great way we can tell the compiler more about our code. I encourage you to use them whenever you find yourself in a similar situation in order to reduce the need for type assertion. In this video, we learned how to use user-defined type guarding to remove the need for an additional type assertion. In the next video, we're going to look into using multiple function signatures. In the previous video, we looked into using user-defined type guarding. In this video, we're going to keep working with the type system and look at how we can use multiple function signatures in TypeScript. Let's take a look at multiple function signatures, optional parameters, default parameters, and some alternatives we can use to multiple function signatures. Overall, we're going to step through an example to work through these topics. Let's take a look at food item storage. Food item storage is a simple class that interacts with the file that holds all the food items. We're going to work on changing the list method's function signature. For the purpose of the example, I've removed the method's body so we can focus on the function signature. I've added this dummy code below, but that's just to prevent the compiler from throwing an error because a return type isn't specified. For our example of changing this method, we're going to implement two kinds of filters. One, a name filter. Two, a food item status filter. Let's come up with some requirements we'll implement with these two parameters, and we'll write the code for how we'd call this. 1. The list method can take a name parameter. 2. The list method can take a status parameter. 3. The list method can take a name parameter and a status parameter. And 4. The list method should default the status to active if it's not specified. Before we write our function signatures, we'll establish some general rules for doing this. 1. Start with the function signature requiring the least number of parameters and most specific. 2. Work down towards a function signature with the largest number of parameters and most general. 3. Make sure you use signatures in such a way that the parameters can be differentiated by their type. To write this, we'll start with two requirements that only require one parameter, a name parameter and a status parameter. To specify an additional function signature, we just have to rewrite the function signature above the main signature. Here we'll write our name-only signature, then our status-only signature. Note that our return type is a promise with an array of food items. We'll talk about promises in a later video, so for now ignore the return type. Now we can write our signature for when we provide a name and a status. We've written our list of signatures. Now we can write the final implementation function signature that will be used internally in our list method. We have to remember that our compiled JavaScript will have no knowledge of our other method signatures, and so we have to write this in such a way that will work at runtime. We'll look at our first parameter, and we can see above that it could be a name or status parameter. So let's write that and type it with a union type. Our second parameter can only possibly be a status, so we can just name it status and give it a food item status type. You can see we're now getting an error on our first signature, and it's because it's not compatible with our current implementation signature. We need to change our signature to let it know that status is optional. We can do that by specifying a question mark after the parameter name. Now we have to start implementing the body of our method. To do this, we'll need two variables, one to hold the name and one to hold the status. We already have a status variable from the parameter, and so we'll just need to create a variable for the name. Our goal is to now fill in the name variable with the correct name and the status variable with the correct status. Let's start by telling the compiler if the first parameter is a name variable. To do that, we'll just have to type guard the parameter and see it's a string, then assign the name or status variable to the name variable. In this situation, we now know the first parameter is a name variable, and the second parameter could possibly be a food item status. But if that status was provided, it will already be in the status variable. We'll change the code to now handle the situation where a status variable is passed in as the first parameter. To do that, we just have to add an else condition that checks if the type of status is a number, since food item status is an enum, and at runtime enums are numbers. Cool. Now our list method is all set to be able to use the name and status variables. There's one requirement left though, and it's to make status default to active when it's not specified. This would happen when just specifying a name. To do this, we can change our method body to properly assign an active status to the status variable when it's undefined. However, we can more easily solve this by changing the status variable from being an optional parameter to a default parameter. We've now implemented the requirements for our function signatures, and from here on out we just have to implement the rest of our method, but we won't cover that in this example. Even though we looked at how to use multiple method signatures, I would personally recommend not using them, except in the simplest cases. Generally, it's much better to create separate descriptive methods, like a list by name, list by status, and a list by name and status method, or better yet, one method with one filter parameter that is an object with optional properties called name and status on it, as shown in this example. This is much simpler, and it's difficult to make a mistake here. In the next video, we're going to look at using rest parameters and the spread operator. In the previous video, we looked at how we can use multiple function signatures. In this video, we're going to look at using rest parameters and the spread operator. A rest parameter is a way to specify that a function should allow an indefinite number of parameters. To demonstrate this, let's add a new method to number helper that will get the sum of all the number arguments supplied to it. We'll call it sumParams, then create a rest parameter called numbers. You can see we specified it's a rest parameter by adding 3 periods before the parameter name. Additionally, we've typed it as a number array because a rest parameter will contain multiple values in the form of an array. One note about a rest parameter is that it must be the last parameter specified. You can see by adding a parameter afterwards, we got an error. But it's perfectly fine if we move this before the rest parameter. Now we can go ahead and implement our method that will add all our numbers together. Here we're using the reduce function in JavaScript to calculate the sum of the numbers array. We can now use our newly created method and specify as many arguments as we want to it, and still have strong typing. Now that we have this method, say we wanted to pass an array of numbers to it instead. You can see this code errors because our number array is not assignable to a number. To solve it, we can use a spread operator, and doing that is very simple. We just specify 3 dots in front of our array. This will pass the values of our array into sumParams as individual arguments. We could then also add even more arguments, no problem. The spread operator also allows us to do other neat tricks, like combining multiple arrays together. We could even do a more complex example, like this. This creates an array first containing the number 4, then the values in the nums array, and finally the spread operator will pass our new array into the function as individual parameters. In this video, we have looked at using rest parameters and the spread operator. In the next video, we're going to look into extending built-in types. In the previous video, we looked at rest parameters and the spread operator. In this video, we're going to look into extending built-in types. First, we'll look at an example of adding a function to a built-in type, and then we'll look at how we can easily extend built-in types starting in TypeScript 1.6. Sometimes JavaScript developers like to add functions to objects they don't own. For example, adding functions to the date prototype or number prototype. This is widely considered as bad practice because it adds risk and makes the code harder to maintain. It creates the opportunity for the same function name to have two different implementations, causing bugs that are difficult to track down. Regardless of this, it's still useful to know because sometimes it's necessary, like when creating a jQuery plugin. In our application, we have the requirement to convert a number to a currency value. We're going to show how we could do this by adding a format as currency function to the number prototype. So to do this, we assign a function to the format as currency property on the number prototype. It's important to use a function expression instead of an arrow function because we have to capture the value of this within this function block and not use the value of this from outside the function. Then in our function expression, we just have to return the number formatted as a currency value. Here our currency formatting is very simple, and it just returns a $sign and the number with 2 decimal places. There's a problem though. TypeScript is telling us that format as currency doesn't exist on number. To fix this, we have to use declaration merging and define an interface with the same name as the number interface. Then add our format as currency function and say it returns a string. We're still getting an error though. This is because since we're using external modules, this number interface is not visible elsewhere in the application. We have to merge it with the number interface at the type definition level. To fix this, I've created a TypeScript definition file called number.d.ts, and now we can put the number interface with our new format as currency function in here. We're going to go into TypeScript definition files more in the next section. Great, now our error's gone. We can now use our new method variable typed as a number. Here's an example storing the number 5.2 in a variable and then calling format as currency on this variable. As we discussed though, doing this isn't good because another developer might override our format as currency function with their own. This is why in our application, we are instead using a helper class with a format as currency method defined on it. You can see that here in the number helper file. Starting in TypeScript 1.6, there's a new way we can work with built-in types, and it's by extending them with a class. This is very useful on certain built-in types, especially the error type. Here's an example where we define our own class that extends error and takes an error code. For the example, the error is being thrown, then caught, and it displays the message if the error thrown is a my custom error with the error code error2. In this video, we looked at adding functions to built-in types, and then at extending built-in types. In the next video, we're going to look at how we can refactor code because of the type system. Hello and welcome to the final video of Section 4 on interacting with the type system. In the previous video, we learned about extending built-in types. In this video, we're going to look into code refactoring. First, we'll look at what code refactoring is. Then we'll look into using automatic code refactoring, and finally discuss how TypeScript helps us when we manually refactor our code. Code refactoring is a useful concept that allows us to quickly change our code without changing its behavior. This is incredibly useful for improving the readability of our code. Previously in JavaScript, if you wanted to make a change to a variable name, we would have to find and replace all matches of a particular string. Sometimes this works out okay, but not always. Additionally, our only line of defense would be our unit tests and general testing. TypeScript really came to save the day for doing massive code changes without finding out about mistakes later. In TypeScript, code refactoring is less risky and easier than in JavaScript, especially when we avoid the any type. Automatic code refactoring support varies based on the development environment being used, and so you should do some research on what yours supports. In these videos, I've been using Visual Studio, which allows renaming identifiers easily with keyboard shortcuts like F2, or by right-clicking the identifier, going to Refactor, and then clicking Rename. Currently, reordering of parameters is not supported in Visual Studio. In this example, we're going to change this dateHelper's toShort method name to have a similar name to toLong datestring above, because it's a bit more descriptive. Currently, if we right-click this method name and select Find All References, we can see all the places where toShort is being used. Alternatively, we could have used the keyboard shortcut Shift F12 or done the sequence Ctrl-K, then Ctrl-R. Let's go ahead and rename this to toShort datestring. So I'll right-click this method name, go to Refactor, Rename, and then type in our new name. Great. Now if we find all references, we can see that our previous references are using the new method name. Manual code refactoring in TypeScript is easy because the type system tells us when we forget to change something. For example, if we were to move toShort datestring to another file for some reason, we get errors on all the parts of our code that used to reference it. We would just have to go through these errors one by one and change everything to be correct. Previously in JavaScript, we would have to be diligent to make sure we have updated all the places in our code that use this method. In this section, we have looked into interacting with the type system. We started with type assertion and then looked at type guarding in depth, then at multiple function signatures, advanced function use with rest parameters in the spread operator, extending built-in types, and finally code refactoring in this video. In the next section, we're going to look into representing JavaScript libraries with TypeScript. Section 5 deals with representing JavaScript libraries. In this section, we'll look at what definition files are, then at how to write one, strong typing JavaScript libraries on the run, downloading and managing definition files, and finally, a video on included definition files. Now we move on to the first video of this section that deals with definition files. In this video, we're going to look at what definition files are, then at an example of compiling some of our TypeScript code to produce a definition file. While programming in TypeScript, we will come across times when we have to reference JavaScript code in our TypeScript files. There's a problem with this though. The compiler doesn't have any knowledge of this code, and so it thinks we're using undeclared identifiers. Supplying it the JavaScript file won't help. We have some options we can use to overcome this problem though. We can 1. Convert the JavaScript to TypeScript, or 2. Tell the TypeScript compiler about the JavaScript. In situations where we are the original code maintainers, it might make sense to convert the JavaScript to TypeScript. However, in situations where someone else is maintaining the JavaScript code, it more than often makes no sense to do this, unless we can convince the original code maintainer to start maintaining the code in TypeScript. The problem with converting JavaScript code to TypeScript when we don't maintain the code is that overall there are now 2 separate pieces of code to maintain, and it makes it difficult to take advantage of new changes the maintainer makes to the original JavaScript code. Additionally, it can sometimes be a lot of work to convert the JavaScript to TypeScript. In this section, we're not going to look at converting the JavaScript to TypeScript, and instead we'll focus on the second option of how we can tell the compiler about the JavaScript. So how do we tell the compiler about the JavaScript code? Well, it's quite simple, and it's to use a definition file. A definition file can be used to describe the structure and type information of JavaScript code. Put more simply, it describes the shape of JavaScript code, so that we can use it with strong typing in TypeScript. A definition file also contains only a subset of TypeScript language features. Those language features being the only ones concerned with describing the shapes of objects. So because of this, definition files won't be compiled in the final JavaScript, as they are only used in helping compile other TypeScript code. To demonstrate a TypeScript definition file, we're going to work backwards from what we've been discussing and generate definition files from our TypeScript code. We've looked at number helper before. Its structure is quite simple. We have a class, and for this video we're only going to work with the format_as_currency static method. Format_as_currency accepts one number argument and returns a string. Let's compile just this file now. To do that, I'm going to open up the command line to the folder number helper is and compile number helper by running tsc numberhelper.ts -d for declaration, -m for module, then AMD. After it's done compiling, we can open up the generated definition file for number helper. It's created in the same folder with a similar file name, but it has the .d.ts extension, which means it's a TypeScript definition file. Let's take a look at this file. As you can see, this file contains the necessary information to provide the structure and type information of our compiled JavaScript. It has our class numberHelper, our static format_as_currency method, and it describes how format_as_currency takes one parameter called val, that's a number, and how it returns a string. So that's it. That's what a definition file looks like. In this video, we have learned about what a definition file is and how to generate definition files from our TypeScript code. In the next video, we're going to write a definition file from some existing JavaScript code. In the previous video, we looked at what definition files are. In this video, we're going to write a simple definition file. First, we'll look at some resources we can study to get more information about writing definition files. And second, we'll go through a simple example to show off the basics of writing a definition file. For more information about writing definition files, I would recommend checking out the TypeScript handbook and look at the section that deals with writing .d.ts files. The TypeScript handbook is also a great resource for a lot of topics about the TypeScript language. Additionally, check out Definitely Types guides. They have a good best practices section that could help you learn a lot by reading it over. For anyone not familiar with Definitely Typed, it's a resource containing a large amount of TypeScript definition files that are maintained by the TypeScript community. We'll talk about the importance of Definitely Typed in a future video, but for now just know it's where everyone comes together to share and maintain TypeScript definition files. Let's now move on to writing a definition file. To write a definition file, it's recommended to first take a look at the documentation, and then write some tests from that documentation. The tests aren't runnable, like how you would run unit tests, but instead it's a file that contains code that should compile. Similarly to unit tests though, we should cover every situation of using the code as possible. The final step in this process is to write a definition file that fulfills the tests. For our example, we're going to look at writing a definition file for a very simple Node.js library called rimraf. Rimraf is used to force the removal of directories and their contents recursively. It's essentially equivalent to the Unix command rm-rf. We're going to write the tests for this in the typing/rimraf directory of our server app. We'll call the file rimraf-tests.ts to keep in line with Definitely Types contribution guide. First of all, the documentation for rimraf is very simple. From it, we know that rimraf is an external library, so let's import it by writing import *as rimraf from, and then rimraf in quotes. Deciding how it should be imported can be found out by looking at the documentation, or by looking at the source code. Don't worry if you don't understand external modules yet. We'll have a video on ES6 modules in the next section. Next, if we look at the documentation, we can find out it's a function. So let's use rimraf as a function. Now from the documentation, we know that the first argument is a string that's a path. So for our test, we'll provide it any string. Note that it doesn't matter what string we provide it with. In the end, the tests are only there to be compiled, and they won't be run. The documentation then tells us that the second parameter is a callback function, and that this callback function will be called with an error object if an error occurs. We're mostly all done with the rimraf function, but the documentation tells us one more thing. There's a sync function defined as a property on the rimraf function, but it only takes one string parameter, and that's a path, like the first parameter of the rimraf function. Good. We're done writing all our tests, and we've covered all the possible scenarios to use this library. Now our only goal is to write a definition file so this code will compile, and we'll do this in rimraf.d.ts in the same folder as we wrote our tests. We're going to use our tests for reference as we do this. So the first aspect of rimraf we should look at is how it's used in other files. We can tell from our import statement in our tests that it's an external module. To define that, we'll write declare module and then rimraf in quotes. The word declare signifies that it's a TypeScript ambient definition and that it represents an object that exists outside our TypeScript code. The quotes signify that rimraf is an external module and not an internal module. That will make it work with import statements, and we can see that this error in our tests has already gone away. If we hadn't have used quotes here, you can see that the error returns. Next, let's tackle the fact that rimraf is a function. To do that, we're going to write a function without our parameters for now. And remember that we only have to write the function signature because we're only dealing with the shape of the rimraf library. Now we can export our function from our module by using export equals and then our function name. Exporting is necessary because nothing inside a module is visible outside a module until it's exported. Now we can write our first parameter, which is a path that's a string, and our second parameter that's a callback that has an error as the first parameter. Finally, our last requirement is to write the sync function that's a property on our rimraf function. We've already defined a function here for rimraf though, so how can we define a function that's a property on another function? Well, we've talked about declaration merging before, and we can use that same principle here to merge a function with a module, and then in that module, we'll define our sync function. To do that, we can simply write a module in the same scope with the same name, and then export a function called sync from this module. Additionally, we'll make sure our sync function signature is properly defined to have one path parameter that's a string. This module merges with our rimraf function, and when that happens, our function gets this sync function defined on it as a property called sync. Great, so all our tests pass now, as the compiler sufficiently knows enough about rimraf. Rimraf can now be used in our application with the benefits of TypeScript's strong typing. Using this information, you can use similar techniques for when you create definition files, and I would encourage you to use this skill to write and contribute to definition files on Definitely Typed. In this video, we looked at the basic process of creating a TypeScript definition file. There's lots of more advanced scenarios though, and for that, I recommend taking a look at the resources we showed earlier on in this video. I also recommend learning by doing, and if you come across any problems, you can ask or search for help online. In the next video, we're going to learn about strong typing JavaScript libraries on the run. In the previous video, we looked at writing a definition file. In this video, we're going to look at some strategies for using JavaScript libraries when nobody else has written a definition file, and you don't have the time to write an extensive definition file yourself. First, we'll look at one approach to doing this that is quick, fast, and easy to get the compiler compiling. And then we'll look at using an approach that's more maintainable and gives us the benefits of strong typing. Sometimes not finding an already written definition file can be frustrating enough. We want to get some code written, but instead we're stuck having to write a definition file. Let's look at our datehelper.ts in our web app. Datehelper contains all our date-related functions, and behind the scenes, it's using moment.js. In the format method, we can use the passed-in date and format string, and pass that to moment.js for it to format the dates for us based on this criteria. In this scenario, a definition file does indeed exist for moment.js, but I've removed it from our application for the sake of this example. So say we don't have a definition file, and we want this code to compile. What are our options? Well, a quick and easy way to get coding is to declare a module in our definition file, like in the last video, but export a variable typed as any from it. Now our compile errors have gone away, and we can use the moment module in any way we like, and the compiler will trust that we're doing everything correctly. Take note that in this scenario, had we not been using external modules, we could simply use an ambient variable definition by doing declare var moment and then type it as any. Remember that when not using external modules, the code will compile fine across all files that use moment if we write this in our TypeScript file, but I would still recommend putting all these definitions in definition files in order to keep everything organized. Getting back to exporting a variable typed with the any type, this technique is good for using an existing JavaScript library quickly in our application, but by doing this we've lost type safety. We can now easily write code that will only throw an error at runtime, and additionally, our format method's return type on datehelper is now the any type. To fix that, we'd now need to explicitly define the return type, a format, to be a string. And if we were to use the moment module in multiple places of our application, we'd find ourselves having to be explicit or use type assertions quite a lot to maintain typing. Let's admit that this isn't the end of the world, but as we strive to write better code, what's a better approach we can take? Well, the approach we can take is the title of this video. That is, we can strong type our JavaScript libraries on the run. To do that, we'd only type the functionality we need as we use it in our application. Let's replicate the code we use in our application and move it into our moment.tests.ts file. There's only 2 lines in our application that reference moment. The first is the import statement, and the second uses moment as a function and passes in one date parameter. That function then returns an object with a format function that takes a string as its only parameter and returns a string. There's obviously a lot more scenarios that these 2 functions could take, but right now we're only interested in outlining the functionality we're using in our application. We can add more at another time if we need it. Now that we have the functionality we're going to use defined, let's finish off our definition file. We'll remove the any type and replace it with a function type that takes a date and then returns an interface that we'll call moment_static. Now we can define our interface and make it have a format function on it. Great, we're all done, and our format method will now correctly know that the return type should be a string. Now if we ever come across the scenario that we wanted to use more functionality from moment.js, we would look at the documentation, write a definition file test, and then add the method to our definition file on the fly. Obviously though, remember that someone else has already done the hard work, and a complete moment.js definition file is already available for us to download in this situation. We're going to look into this more in the next video. In this video, we have looked at strong typing JavaScript libraries on the run. You now know how to yet again avoid the anytype. In the next video, we're going to look into downloading and managing definition files. In the previous video, we learned about strong typing JavaScript libraries on the run. In this video, we're going to look into downloading and managing definition files in our application. First, we're going to look at manually downloading definition files, and then we'll look into using the TypeScript definition manager. As long as a definition file exists, it will most likely be able to be found online, and one of the best places to look is definitely typed. As discussed before, definitely typed is a collection of TypeScript definition files created by the TypeScript community. TypeScript definition files of many JavaScript libraries can be found on here. The address is definitelytyped.org, and on here is a section on getting definitions. There's three main options for getting a definition file. The first is to visit the GitHub repository. In here is a list of TypeScript definitions. For example, if we wanted to find definitions for a specific library, like React, we could search for it. Then go into the folder to get the type definition. In this folder for React, we could open up react.d.ts and then download the raw file and include it in our application. We can see here that this TypeScript definition file is for this version of React. But what if we wanted an earlier version? Well, the solution isn't too great here, but we would just have to go through the history of this file and find an earlier version. Let's go back to definitelytyped.org. So the second option listed is to use a NuGet package. I'm not going to get into how NuGet works because it's Visual Studio specific, but if you're using NuGet already in your application, just be aware that you can download and manage TypeScript definitions easily through NuGet. Now we're going to look at the final option presented here, and it's an option that works well with any development environment. It's using the TypeScript definition manager. The TypeScript definition manager, commonly referred to as TSD for short, is a utility that allows us to manage TypeScript definitions in our application, similarly to how we can manage node packages with the Node Package Manager, otherwise known as NPM. For this example, we're going to install jQuery's TypeScript definition file. To do that, we first need to install TSD globally. So run the command npm install -g tsd. Now say we had never managed our application with TSD before. We would need to initialize our application to have a tsd.json file. This file is similar to a package.json file in npm in that it holds a reference to the specific version of a TypeScript definition file to use in an application. Doing this is easy. We just have to enter the command tsd init, which, as you can see, has written our tsd.json file and a typings/tsd.d.ts file that contains references to any definitions we want to install with tsd. Now that we have everything initialized, let's search for jQuery's type definitions. We can do that by writing tsd query and then the name of the definition we're searching for, so in this case jQuery. This found the package we're looking for, but just also take note that we could have searched with wildcards by typing in something like this. But we're only interested in the jQuery type definition package. Let's install it by typing tsd install jQuery, and also add the Save Compiler option to specify that it should save this information in our tsd.json file. Now we can open up our tsd.json file and see that the jQuery definition file is specified in here, and we can also find the actual definition file in typings/jQuery/jQuery.d.ts. One great feature of using a tsd.json file is that we can ship our packages without the type definitions, and then have them installed by running a command in tsd. For example, if we delete our typings folder, we can run the command tsd install. And all our packages stored in tsd.json are back in our application's typing folder. Overall, there's a lot more features to tsd that hasn't been discussed in this video. It's best if you read the README found at github.com/definitelytyped/tsd to learn about a lot more of the functionality that tsd has to offer. In this video, we have looked into downloading and managing TypeScript definition files in our application. In the next video, we're going to look at some definition files that are included with TypeScript. Hello and welcome to the last video of this section on representing JavaScript libraries. In the previous video, we looked at downloading and installing definition files. In this video, we're going to look at some definition files that are included with TypeScript. First, we'll look at where we can find these definition files. Then we'll look at lib.d.ts. And finally, we'll look at how we can modify lib.d.ts. When programming in TypeScript, it's sometimes useful to understand how parts of the JavaScript language are defined, or to change these definitions because the runtime environment you're using requires different definitions. In TypeScript, the definitions for parts of the JavaScript language are defined in definition files, so it's easy for us to look at these files and understand them. These files are included with TypeScript, and they're currently found in the lib folder of TypeScript source, which can be found on its GitHub page. In here, the definitions are divided up into multiple files, but the build concatenates them into a file called lib.d.ts. We're going to look specifically at lib.d.ts because it's the file we can take a look at while writing TypeScript. Here in our number helper class, there's a toFixed function on this variable typed as a number. The reason this is able to not throw a compile error is because this function is defined in lib.d.ts. We can see that by right-clicking on this function name and then clicking Go to Definition. Alternatively, in Visual Studio, we could have just hit F12. This has taken us to its definition in lib.d.ts, and in here we can see there's a toFixed function defined on the number interface, which is what all number types use as their prototype. Let's have some fun now and change the lib.d.ts file. I'm going to comment out this method and save this modified file in the typings directory of our web app. Cool. Now let's use our build script and try compiling. In this case, the compiler will see the file lib.d.ts in our application and uses that instead of the standard lib.d.ts that ships with TypeScript. That might not work in all scenarios, so you might need to compile with the nolib compiler option, which excludes lib.d.ts when compiling. Now if we compile by running the TypeScript gulp task in our web app by running the command gulp TypeScript, we can see there's a new error, and it's saying the toFixed function doesn't exist on the type number. This is expected because for this example, we commented out the toFixed property in order to deliberately cause this error. Although this is not very useful in this scenario, there might be other scenarios where certain JavaScript features differ in a different runtime environment, and you want to reflect that in the definition file. This technique can be used to modify the definitions that the compiler uses by default. Although using a custom lib.d.ts can be useful in some scenarios, you have to keep in mind that all the code going through the compiler will now use your custom lib.d.ts. And this might break code other people have written who are not using your same lib.d.ts file, or cause your code not to compile for them. As long as you are aware of this fact, it shouldn't be too much of an issue. In this section, we looked into representing JavaScript libraries in TypeScript. First, we looked at what definition files are, then at how to write one, strong typing JavaScript libraries on the run, downloading and managing definition files, and finally this video on included definition files. In the next section, we're going to look at some language features we can use to improve the code we write. Hello and welcome to Section 6 of Mastering TypeScript. In the previous section, we looked at representing JavaScript libraries. This section is on some language features in TypeScript that we can take advantage of to improve our code. In this section, we'll look at making the most of let and const, working with strings, look at enums, then const enums versus enums, moving to ES6 modules, and finally a video on destructuring. Now we move on to the first video of this section, and it's on making the most of let and const. In this video, we're going to take a look at what some of the problems with var are, then at using let and const instead. When first getting started with JavaScript, developers who come from a background working with languages such as C, C#, or Java sometimes get confused with how scope works in JavaScript. For example, take a look at this code showing on the screen here, and say to yourself what it outputs. Pause this video and give it a better look over if you have to. This code, when run, outputs 3 and doesn't throw an undefined error. The reason why this happens is because variables in JavaScript are function scoped and not block scoped, so the variable n is visible anywhere within this function and isn't limited to this if statement. Since var is function scoped, it has often been recommended to define all variables a function uses at the start of the function body like this. This is a more readable version of the way we had the code before. It reduces confusion and the chance of defining two identical variables with the same name. This function scoping is somewhat of a problem because it exposes a variable to too much. For example, if we added a for loop here, why would we want the variable I to be able to be used outside this for loop unless we defined it outside? Wouldn't it be better if the language restricted the variable to be used within the for loop? Some other problems with var is that it lets us use a variable within the function scope before the statement that defines it. This compiles and runs without error. Additionally, var doesn't restrict us from redeclaring a definition. We could take this definition for n and write it twice, no problem. Although these problems exist with var, there's a pretty easy solution around it, and it's to never use var. Instead of var, we can use let, which is a new ES6 feature that's available today in TypeScript. Let is a keyword we can use to define variables, but there's a few improvements. You can see if we change the vars to lets in this example that a few things will happen. First, we're getting an error on the first line about using n before we've defined it. Second, we're getting an error about redeclaring n. And third, we're getting an error here about how it can't find I. The reason for that is because I is block scoped, and so the variable only exists within the scope of a block, and not the scope of a function. By block, it generally means from the start of the statement with the open brace to the end of its corresponding close brace. So there's a block at this if statement, block at this for loop, and then a block for the entire function. For another example demonstrating this block scoping, we could define a variable within this if statement, and then we can see we can't use it outside the if statement. The restrictions we get using let are all good because it helps us catch mistakes quicker, and since our variables are now block scoped, we don't have to keep the convention of defining all our variables at the top of the function body. Instead, we can define them closer to where they're used. There's one more restriction we haven't talked about that we can take advantage of here, and that's to use const. Const works similarly to let, but there's one major difference. Const holds a read-only value, and it won't let us change that value afterwards. For example, if we do a const declaration and then try to assign it a value later, we'll get an error that the left-hand side of our expression can't be a constant. You can make your own coding standard of when you would like to use let or const, but my recommendation for a coding standard is as follows. 1. Use const when possible. 2. Only use let when the variable will be assigned a new value later. And 3. Never use var. These same recommendations can be found in a lot of ES6 style guides online, and can be easily enforced with a linter like tslint. In this video we have looked at how we can use the let and const keywords instead of var in TypeScript. I hope you will start to get in the habit of using them from now on. I know it can be challenging after being so used to using the var keyword. In the next video, we're going to look at some better ways of working with strings in TypeScript. In the previous video, we looked at using let and const instead of var. In this video, we're going to look at better ways we can work with strings in TypeScript by using template strings. We'll look at using string interpolation, multi-line strings, and tagged templates. TypeScript yet again brings some new JavaScript features from ES6 that we can take advantage of today. This time it's template strings. Template strings are denoted by surrounding the string in backticks instead of single or double quotes. The first clear advantage that can be seen here is that we can now easily use single or double quotes in our string without having to escape them. Backticks are used far less frequently in most strings we have to create, and so they make perfect characters for denoting the start and stop of a string. The best part about template strings is they allow for string interpolation, which is a fancy way of saying it now allows us to easily have expressions in our strings and have static typing within these expressions. Take this example in base logger. This method log request is passed in a request, and from that it logs a string that includes the IP address and URL that was requested. Previously we would have had to concatenate this together or use a custom string formatter function, but template strings allow us to insert these variables by surrounding the expression in braces and preceding that with a $sign. Behind the scenes, TypeScript will compile this to use string concatenation when targeting below ES6. One neat thing about this is that we aren't limited to just using variable names. We could put any expression that returns a result. For example, we could get the result of a function, or even add numbers together. One other aspect of template strings is that they now give us a new way to do multi-line strings in JavaScript. Previously, if we wanted to make our string span multiple lines in a JavaScript file, we would have to use either string concatenation, put a slash at the end of each line, or come up with other creative ways for doing it. Template strings are very much like this second example, except now we don't have to bother putting the slash or new line character at the end of each line. There's something we need to watch out when doing this, though. In both our second and third example here, the string is including all this white space before the first character on the second line. We can solve this problem by removing the white space at the start of this line. However, relying on having to inspect the white space isn't ideal, and having this code start at the beginning of the next line doesn't look very nice, especially once the code starts getting indented out to the right enough. It's for these reasons that I would recommend sticking with string concatenation in most situations, and using either template strings or strings denoted by quotes, depending on the situation. It's important to stress that in certain situations, multi-line templates are more appropriate, and make the code easier to manage. The last new feature that template strings bring us are tag templates. Tag templates allow us to modify how templating happens on a string. Let's take a look at a simple example of writing a tag template that bolds only the values provided to the template string. For example, we'd wanted to put in our variable something like what we have in this comment. To create the base of a tag template, we need to create a function and reference that function name before a template string we can use it on. We've already created the function without the body here at the top, and so we can pass this template string through this selective bold function by referencing selective bold before the template string like so. The standard function header for a template string is to have the first parameter as an array of strings, and then following that is an indefinite amount of parameters that are the result of expressions within the template string. Notice how we used a rest parameter that we learned about in section 4 in order to specify an indefinite amount of parameters. Note that these values are typed with the any type. The reason for that is we want to allow someone to use any type of value within our template string. If we wanted, though, we could restrict that. We could set the type to a number array to only allow numbers, or set the type to a string array to only allow strings. You can see that when using the string type, the number used in this expression now throws a compile error, because this tag template now expects only strings to be provided. Also take note that we don't necessarily need to return a string in this function. We could return any object of any type that we want. In our example here, the variables will contain the following information as shown here in the comments. So we can now use this information to loop through these arrays in such a way that we build a string that wraps the values in bold tags. You can see here that it's looping over the two arrays in parallel, appending the string as is, and wrapping the value in bold tags after it. Now when we run this code, we can see that our provided value is being wrapped in the bold tags. There are many other uses of tag templates. I would recommend you research this feature more online for a few more ideas. In this video, we have looked at working with strings more effectively in TypeScript. In the next video, we're going to look at enums. In the previous video, we looked at how we can work more effectively with strings. In this video, we're going to look at how we can effectively use enums in our code. We're going to take a look at what an enum is, how it helps us, and an example of using an enum. In code, we sometimes want to represent a limited set of constant numbers in a readable way. As you know, in our sample application we store orders, and those orders have an order priority that can be low, medium, or high. Here's a function that maps our order priority values to strings. When order priority is 0, that means it's a low order priority. When it's 1, it's a medium priority, and when it's 2, it's a high priority. There's some problems here though. First of all, what happens if for some reason we need to change high to be 4 instead of 2? Well, that would be a bit of a problem, because we would have to change everywhere else in our application where the number 2 is used to represent a high order priority. So how can we solve this problem? Well, we could store our values as constants in another file, and name the constants after our high, medium, and low order priorities. This isn't actually too bad. Now we have some constants we can use in our function. Let's go ahead and use them in our file now. This is great. Now these constants are grouped together in an order priority module, and when we go to use an order priority, we get code completion listing all the possible options. There's still one problem. Our getOrderPriority string accepts a number type. Wouldn't it be great if we could instead specify that this function takes an order priority instead of a number? Well, we can, and to do that we can use an enum. An enum is a type that represents a set of constant numbers in a readable way. Let's change our list of order priority constants to be an enum. And to do that we write enum order priority open brace, and then we can change these constants to instead be values on our enum. And finally we can export our enum from our file. We're done, and you can see that this is a better solution than before, because now our function has the additional information that the order priority variable should be one of the values in order priority, and we have still maintained the constant nature of these values. For example, we wouldn't be able to assign a new value to order priority.high. Looking back at our order priority enum, an important point to note is that we've decided to explicitly define the values of each member, but it doesn't have to be that way. We can remove these explicit values, and now they'll automatically be assigned by the compiler. In this case, it happens to also be with the values 0 for low, 1 for medium, and 2 for high. We can tell this by looking at the generated code or checking their values at runtime. Or it will tell us the number value when we hover over the enum value, depending on the editor. Since we are storing the value of order priority as 0, 1, or 2 in the database, not explicitly defining our enum member values in our application creates risk. For example, say we had a new requirement to add very low order priority. We might go ahead and add very low to the top of that enum. But there's an issue with this. The underlying values of the enum have shifted so that low is now 1 instead of 0, medium is 2 instead of 1, and high is 3 instead of 2. This matters because now all our order priority values are different than what's stored in our database. Had we explicitly defined our enum values, this mistake would have been much harder to make because the values of the enum members wouldn't have been automatically set in the background. Another advantage to explicitly defining enum values is that we can skip values. This is an enum used to represent our possible order status values. On here is a lost status, but it's commented out. This is because the lost status is a remnant of when lost orders were a part of daily life at Slice It Pizza. However, customer service has improved, and lost orders are now part of the past. We can see here that an advantage with explicitly defining enum values is that we can remove members without changing the values of the following members. For example, cancelled is still equal to 5 and was not automatically changed to 4. Note that explicitly defining enum values is only useful when we care about the number value in the enum. In this video, we have looked at improving our code with enums. In the next video, we're going to look at what const enums are and how they differ from regular enums. In the previous video, we learned about enums. In this video, we're going to expand on that knowledge and look a bit more at how enums work, then at how const enums work, and then look at their differences. Here in our application, we once again are looking at our order priority enum, but on the right side, we have the JavaScript output of this TypeScript code. It's kind of hard to read though, so I've included the JavaScript object this code creates here in a comment. As you can see, behind the scenes, once compiled, the order priority object will have 6 properties, and not just 3. It has its regular value declarations here, then its reverse mapping up here. Using this information, we can do things like enumerating through the keys of this object to get all the values. This can be very useful in certain circumstances. Now let's make a slight change to our enum, and make this a const enum by adding the const keyword before it. You can immediately see that our enum has disappeared from the JavaScript output. This is because const enums are not an object at runtime, unlike regular enums. You can also see here that the compiler has replaced our reference to order priority low with the number literal 0. This is how const enums work in TypeScript. The enum value will be inlined into the code at compile time. So how is this useful? Well, sometimes the emitted JavaScript object for our enum isn't necessary for us to have. When that happens, we can benefit from slightly smaller file sizes because the compiler replaces many characters with one or a few. Additionally, depending on how we package our code, the files that contain our const enums are no longer necessary to visit at runtime. Here's a function that gets the value from an enum. It does that by getting the object's keys and then filtering them for properties that parse to a number. For example, with our regular order priority enum, it would return an array with 0, 1, and 2. Now let's pass in our const enum, and immediately we see that it errors. Well, why is that? We can get a hint by looking at our compiled JavaScript and see how an order priority reference is being passed in, but no order priority variable exists in this JavaScript. We also get an error message saying the only times we can use a const enum are in an export or import statement, or by accessing the values through a property or index access expression. This makes sense because of the nature of const enums, and it's additionally why we can't assign the order priority enum to a variable, or say a variable will be the type of the enum. To fix all these problems, we can simply make the enum not a const enum. Now the enum itself, and not its values, can exist in runtime expressions. Choosing between a const enum and an enum is up to you. A simple guideline could be to make all enums constant until it's necessary for them not to be. In this video, we looked at the difference between enums and const enums. In the next video, we're going to look at moving to ES6 modules. In the previous video, we looked at the difference between enums and const enums. In this video, we're going to look at ES6 modules. We've looked at ES6 modules a bit before, but this video will look at the feature more in depth. In addition to plain exporting and importing, we'll look at exporting by default, selective importing, bare importing, and re-exporting in this video. One of the best features of TypeScript is that we can use new JavaScript language features that aren't supported in many runtime environments yet. ES6 module support is another great example of that. For the scope of this course, it's assumed that you're already familiar with modules. And so in this video, we're going to just focus on the details of how we can make modules better by using ES6 modules. Once again, for this video, we're going to look at Number Helper. Number Helper is a simple class that we use to accomplish several tasks when dealing with numbers in the Slice It Pizza application. For the purpose of this example, I've reverted the code back to the old way of using require statements instead of ES6 modules. Let's review the old way of doing things, and there's two possibilities. First, there's using an export equals statement, which we're currently doing here. This allows us to export an object from the file so that when we import it here, it will assign our class type to the number helper reference directly. This is useful when we just have one export. The second way of doing things is to export values as properties of a module. So an example of this would be exporting our class by adding the export keyword in front of it, and then as an example, let's create another class above this and export that too. Now you can see that when we require this file, we have two options in IntelliSense. So how can we replicate these two techniques using ES6 modules? First, we'll look at replicating the export equals statement. In ES6 modules, instead of doing export equals, we would instead do export default number helper. Or similarly to export equals, we could also move the export default part right to the class definition. This is a default export, and a default export means that when we import our module, it will use this export by default. You'll see what I mean more by that once we get into the next example with multiple imports. Now our import isn't working well because we haven't changed it to import using ES6 modules. So let's go ahead and upgrade this import statement to use an ES6 module import. To do that, we'll instead write import number helper from, and then the same path as before. Now our import statement puts what we exported by default into this number helper reference. You can see that this works very similar to before with export equals and require, but the syntax has just slightly changed for the better. So moving on to how we export multiple values from our file, let's first restore the code in number helper back to the example of when we had two classes. We'll export our example class above it again, and change our number helper to be exported not by default. Exporting this way is often called a named export. Since we made this change to use named exports, we're now getting an error at the import, and it's because we haven't specified a default export in our number helper file. We could go ahead and define one of our exports to be the default export in order for this to work, which would be perfectly legal. But for this example, we're going to change our import statement to import these classes in different ways. A neat thing about named import statements with ES6 modules is we can now just import one of these classes. Being able to do this is a definite advantage over using require statements. Let's import just number helper for now. To do that, we surround number helper in braces. Good. Now our errors have gone away in this file. Let's go ahead and import myOtherClass as well. To do that, we just have to separate what we want to import with a comma in these braces. Additionally, if we want to rename any of these named imports in our file, we could write the as keyword after the name of the import and then assign it the name we want. That can be useful when two different imports have conflicting names. Now, alternative to this, we could actually just import everything and make it properties of an object. To do that, we would just change our import to be import star as, and then the name we want to give our object, from, and then the path of the file. This is very similar to what we had before with the require statement, as you can see that our two classes are on this number helper object. Another way we can use ES6 modules is to do a bare import. A bare import is different than other methods we talked about earlier because it doesn't add anything to our existing file. Instead, it just runs what is imported. For example, here in app.ts, it does a bare import of this utils/polyfills file that runs any polyfills to fix any unsupported features in our runtime environment. Beyond basic exporting and importing, ES6 modules also allow us to easily re-export modules. This is useful in times when we want to group modules from many files together under one module while maintaining them individually in separate files. For example, here's a way of doing this that re-exports all our enums in a single file. Now when we import this file, we can select the enums we want out of this file without having to write an import statement for each enum. Doing this requires more setup, but can really help with code organization. For more information about re-exporting, or anything else to do with ES6 modules, I would recommend reading the ES6 specification. Let's look at one last question. Should we use default exports, or should we use named exports? The discussion on ES6 modules states that the syntax should favor default exports and imports because they are concise. Personally though, I prefer using named exports almost all the time, except when it makes more sense to use a default export. The reason why I do this throughout the sample application is because the name in the import statement is linked to the name in the export statement. So when I refactor this code by renaming an export, the changes will be reflected in all the files that import my module. This doesn't happen with default exports, as each file gives a name to what it imports that isn't linked to the exported name. In this video, we have looked into ES6 modules. I would recommend you switch to this feature and start using it today. You'll get a lot of benefit out of it in your code. In the next video, we're going to look at destructuring. Hello and welcome to the last video in section 6 of Mastering TypeScript. In the previous video, we looked at moving to ES6 modules. In this video, we're going to look at how we can yet again improve our code by using a technique called destructuring. We'll take a look at array destructuring and then at object destructuring. Previously in JavaScript, when we wanted to swap two variable values, we would have to store the value in the first variable into a temporary variable, then put the variable in the second variable into the first variable, and finally assign the temp variable that now holds the original first value into the second variable. On first glance, it might not look like this code could be improved, but it can. Let's see how. First of all, destructuring allows us to initialize a set of variables based on the values in an array. Let's focus on where we initialize our variables. When we assign 5 and 6 to value 1 and value 2 respectively, we do so on two separate statements, but we can improve this by instead assigning an array of values to a corresponding set of variable names. This is called array destructuring. To do that, we start with a declaration, but instead of specifying the variable name immediately, we instead use array-like notation and specify a set of variables surrounded in brackets. then separate those variable names with commas. We can then specify an actual array on the right-hand side of this expression and match it up with the variable names we want to assign to. So in this case, the first variable name specified will have the first value in the array, which is 5, and the second variable specified will have the second value in this array, which is 6. This is an incredibly useful technique. To further expand on this example, say we had an array with 3 items. How could we get 5 into value 1 and 6 into value 2? Well, we would just throw in an extra comma in the middle. Now the 4 value in the middle will be ignored. Doing this makes sense in certain circumstances, but not here because we are also defining our array. Just be aware that you can do this with destructuring. Now let's focus back on trying to improve our example code. So in this case, we can actually do all 4 of these statements below here in one line. To do that, we can use array destructuring again. We'll define the left side of our expression with the array-like syntax like so, and then assign it an array with the values switched. Great! So now we have used destructuring again to put value 2 into value 1, and value 1 into value 2. You can see that this is quite a powerful feature and really helps to make our code more concise. Now let's look at the other kind of destructuring, which is object destructuring. Object destructuring is similar to array destructuring, but there's a few differences. To demonstrate this, we're going to look at this example. In this case, our goal is to put the properties on my object into value 1 and value 2. You can see we've done that here, the old JavaScript way. So how can we use object destructuring to improve this? Well, instead of using array-like syntax on the left side, this time we can use object-like syntax, like so. Now the corresponding properties in my object will be mapped into value 1 and value 2. What if we wanted to map these out into different names, like first val and second val? How could we do that? You can see we're getting an error when we try this because my object doesn't have the properties with these names. Solving this is quite easy. We just have to specify a name before our variable names, like so. Now our variables are properly mapped to the properties in my object. One caveat to object destructuring is that if we do an assignment without a declaration, then we must surround the entire statement in parentheses. This is required by the ES6 spec, and if we don't do this, then we'll get an error. There are many more neat things we can do with destructuring, like assigning a default value in the case when the value being assigned to a variable is undefined. We're not going to get into these examples in this video, but I'd recommend reading the specification for a complete outline of what's possible. In this section, we have looked at some language features for code improvement. We looked at making the most of let and const, working with strings, enums, enums versus const enums, moving to ES6 modules, and finally this video on destructuring. In the next section, we're going to look at some advanced ES6 and ES7 features. Hello and welcome to Section 7 of Mastering TypeScript. The previous section was on language features for code improvement. This section is on advanced ES6 and ES7 features. This section is going to look at some very new and experimental features currently available in TypeScript. First, we'll look at what generators are and how they improve the performance and efficiency of our application. Then we'll look at writing asynchronous code with async and await. In that video, we'll also look at ES6 promises. After that, we'll have 2 videos on using decorators in our application. Now we move on to the first video of this section, and it's an introduction to generators. We'll talk about what generators are and how the code execution path works when using them. A new feature coming to JavaScript with ES6 is the ability to create generators. Generators are a powerful way to define a function that returns a generator object, and then by using this generator object, we can iterate through its values on demand. Take note though that generators in JavaScript are very similar to what's done in languages like C#, Python, and Ruby with the yield statement. If you're already familiar with that concept in those languages, then that knowledge will be easily transferable here. Here's an example of a generator. To help show how the code executes, I've added console.log statements showing the execution path from 1 to 7. So what's happening here? Well, this getNames function immediately returns a generator object. This happens because we've defined this function as a generator function using the syntax function star. The return generator object is stored on this nameGenerator variable, and the execution continues down until we call the next method on our generator object. Once we do that, the code jumps into the generator function and starts executing. Execution will continue until we hit a yield statement or exit the function. In this case, it hits the yield statement on the second line for the string John. When that happens, the execution exits our generator function and continues executing back at where it was by returning an object from the next function. The yielded value, in this case the string John, can be found on the value property of the object returned by next. So this line will display 3 and then the name John. After this, execution will continue on, but then again, here on this line, execution will jump back into our generator function because we have called the next method on our generator. The execution then re-enters where it last left off and continues down until it hits the next yield statement or the end of the function. In this case, it hits this yield statement for the string Stephanie. Then we exit the generator function again, and the string Stephanie is yielded in the value property of the return object of the next method. Execution continues down, and we once again hit a next method. However, in this case it's a little different. A value is being passed in here, and so when execution re-enters our generator function, the value passed into the next method will be assigned to the variable on the left side of the expression, if one exists. In this case, my value will now hold 964. This is a useful technique for if we ever need to change the internal state of a generator. So now execution continues until we hit a yield statement or the end of the function. At this point, we've hit the end of the function, and so it exits and no value is yielded. It then continues execution where it last left off, and the value property here would be undefined. Note that there's a second property on the object that's a Boolean value called done. As you can probably guess, this Boolean value indicates if the generator is done. In this case, it contains true, since the execution exited the generator instead of yielding a value, but it would have been false in the past two statements. When we run this code, we now see our expected output, where the execution goes from 1 to 7, and John is logged first, Stephanie, our passed-in value, and finally this done value is true, because it's done. The example we have just looked at isn't very typical though. Usually we would have an indefinite amount of values yielded from a generator, and so instead of manually calling next and checking the done property for when it's done, we could use a for of loop. A for of loop works well with generators, or any iterator. It will keep calling next on the generator and provide us with the value property in this variable until the done property is true. In this case, it would iterate all the values from 0 to 1000. To sum up and add to what we've been saying here, generators enable us to easily get an item on demand, and because of that, they don't require us to wait until all the items have been generated before using one item. They also allow us to have infinite sequences. And finally, the last point I'm going to make here is that because they give us one item at a time, that helps to reduce memory usage in our application. We're going to go over this point more in detail in the next video. In this video, we have gone over what generators are and how their code execution path works. In the next video, we're going to learn how we can easily improve performance and efficiency in the applications we write by using generators. In the previous video, we looked at what generators are and how their execution path works. In this video, we're going to talk about using generators to improve the performance and efficiency of our code without sacrificing code readability. First, we'll look at iterating over a set of data that returns an array, then at the same set of data that's instead returned as a generator. We'll go through and compare the two with an increasing number of items. Generators provide syntactic sugar for easily writing performant and efficient code. Let's step through an example that demonstrates that. Here we have two functions. One returns an array of numbers of the specified size, and the other returns a generator object that iterates through numbers to a specified size. In the end, they both return the same data. Now we're going to compare these two methods for their speed and memory use. I have a method called analyze that's going to analyze both functions for us. For this, we're going to use a data size of 1 million items. Let's run this in Node.js and see what happens. Well, it's quite obvious who the winner is here. The generator outperformed the array with a shorter total time to run, and it used way less memory doing it. Just look at how much memory the array used. Now compare that with the generator. In this case, the generator didn't even add anything noticeable to the heap total. Let's increase the number of items to 10 million and run the code. Now you can see the speed on both has increased, but the array memory usage has increased big time, while the generator way is essentially the same. So from this you can see that when using generators, as the size of the data increases, our memory usage stays the same. Remember that these two pieces of code are both looping over the same set of data, and they're both doing the same calculations on it. One more test. Let's make both ways work with 90 million numbers and run the code again. Well, now the obvious has happened, and our environment ran out of memory analyzing our array. However, if we run the way that uses a generator, you'll see it runs no problem once again, and still with the same memory usage. It should be fairly obvious at this point about how generators can help improve the performance and efficiency of our code, and we can do that with barely any effort. There's a lot more that you can do with generators that we haven't talked about. A few additional topics that you can look into are using yield star to yield items from another generator within a generator, using generators with asynchronous code, which is assisted by a topic in a future video that is async and await, returning a value from a generator, and finally using generator comprehensions. Generator comprehensions aren't fully supported by TypeScript yet, but it's a cool feature coming to ES7 that will eventually make its way to TypeScript. You can read about it more by searching online. In this video, we looked at how in certain situations we can improve the performance and efficiency of our applications by using generators. In the next video, we're going to look at an easier way of working with asynchronous code by using async and await. In the previous video, we looked at how we can improve the performance and efficiency of our application by using generators. In this video, we're going to look at how we can use async and await to write asynchronous code. We're going to take a look at using promises instead of callbacks, then at improving our code with async and await. For this video, we're going to look at a very simple example. This function getValue currently uses a callback function to get a value back. In this case, we're using a set timeout within the function. This simulates an asynchronous call to something like a web server, database, file, or some other resource by having a delay before it calls the callback. Let's take some small steps to improve this. First of all, we could use a promise instead of a callback function. A promise represents an operation that hasn't completed yet, but is expected to return a value in the future. In this case, that's exactly what's happening here. So to change this, we'll get rid of our callback function and instead return a new promise. When a promise is ready to return a value, we just have to pass in our value to this resolve parameter, as we are now doing. Since our function now returns a promise, we have to change our function call to handle this. It looks quite similar to before, but now we have to handle the return value in the then function property of the promise. In this situation, our code might seem more complex, but trust me, if you use promises in your application, you will immediately start to notice the benefits. Your code will become much easier to understand and maintain. Okay, now that we're using a promise, let's talk about the subject of this video, which is async and await. So what is async and await? In a nutshell, it's a simple way to write asynchronous code as if we were writing synchronous code. Let's jump right in it. First, we're going to mark our getValue function with the async keyword. This is to signify that this function has some asynchronous code in it. Now we'll change our call to getValue to instead await the value of getValue. Then we'll write this code as if getValue returned a value synchronously. Now we just have to log this returned value to the console. We're getting one more error. And it's because when we have an await statement, it also needs to be in a function marked as asynchronous. Our error has gone away, and we're all done. Now if we run this code, you can see it outputs the correct value of 5. You can see this code is simpler to understand than before. There's no more callbacks, and the promise is hidden away in the function that does the asynchronous work. This video, of course, has been a very simple example of using async and await. If you want to see a more complex example, then take a look through the sample application's code. Take note, though, that the current support for async and await is experimental, and the feature won't be finalized until TypeScript 2.0. Because of this, I wouldn't recommend using it until then. In this video, we have looked at a basic example of using async and await. In the next video, we're going to look at using decorators. In the previous video, we looked at how we can make asynchronous code easier by using async and await. In this video, we're going to look at using decorators to write more powerful applications. We're going to look at what decorators are, then at an example of using a method decorator in our server app. Decorators, sometimes known as wrappers, are a useful tool to easily extend, alter, or document parts of our classes without the use of subclasses, and without altering our method bodies. They allow us to maintain the single responsibility principle in a very easy way. Decorators can be defined directly on a class, and also on a class's properties, methods, accessors, method parameters, and static properties and methods. For this video, we're going to implement a method decorator called log. Every time a method is called that has this decorator, it will log some text that will state the method name, the argument values it was called with, and the return value. Before we begin implementing our requirements, let's review how the different types of logging classes get created in our server app. Mostly, all the objects in the server app get created through the main factory. This factory handles configuring instances of our objects and providing the correct dependencies so that we don't have to worry about it when we use instances of these classes. The two ways of logging are logging to the console or logging to a file. Right now, logging to a file is simple, and we store everything in the same log file. Main factory has 3 methods that relate to these loggers: The getLogger method is used when we want to leave the decision to use a console or file logger up to the main factory, but sometimes we want to be explicit about the method of logging we want to use. In those cases, we can use the getFileLogger or getConsoleLogger methods. Now that we've established how logging works in the Slice It Pizza server app, let's go ahead and implement our requirements. As you can see in the code here, using a decorator is easy, but writing one can be a bit more challenging. Here in log.ts, we already have a function set up for writing a method decorator without parameters. The requirement for a valid method decorator states that the first parameter should be an object that represents the class prototype. Since we want this method to be used on any class, we can use the any or object type here to specify that. Had we want to restrict this to only certain classes, then we could specify that by changing this type. The second parameter should then be a string that represents the property key or method name that this decorator is defined on. Finally, the last parameter should be of the type typed property descriptor, and we've given that a generic parameter of any to specify that we can define this decorator on any method with any type of signature. If we wanted, we could change this so the decorator can be used only on methods with a specific type. For example, we could change it so that it can only be used on methods that have no parameters and a number return type. We're not going to look at all the properties of typed property descriptor in this video, but we will look at the value property of it. The value property contains a reference to the method the decorator is defined on. Using the information we just learned, how can we now write a decorator that will log the method name, argument values, and return type? First of all, we need to override our original method to instead call a custom function, and then that custom function will call our original method. So we're going to save a reference to the original method in a variable, and just as discussed, that's found in descriptor.value. Now that we've saved a reference to the original method, we can overwrite descriptor.value with our own method. Let's do that now. There's 2 points I want you to pay attention to here. First point is that we're using a function expression and not an arrow function. The reason for that is because we want to capture the value of the this reference inside this function, because that will contain a reference to the instance this function is being called on. If we had used an arrow function, then this would refer to window, and that's not what we would want. Second point is that we've used a rest parameter, so that all the arguments this method is called with are now stored in args. So at this point we have the method name, we have the arguments, now we just need the return value. In order to get the return value, we have to call the original method this decorator was defined on. That's contained in the original method variable. To do that, we can call the apply method on the original method function. If you're not familiar with the apply method that exists on all functions in JavaScript, you can go research it online. It's a concept that's been in JavaScript for a long time. Essentially, it allows us to call a function and specify the value for the this reference as the first argument, and then the second argument contains an array of all the arguments we want to pass to the function. Our method is now being called, but we're not capturing the return value. Doing that is easy, so let's do that now. Cool. So we now have all the necessary information we need to log this. I'm going to paste the code that will use our main factory's getLogger method to get an instance of the logger class that should do the logging, then log the information. In this case, it will use the console logger. Now the final step we have to do in order to create a valid method decorator is to return the descriptor. So there you have it. That's an implemented log decorator that logs the method name, arguments, and return value when a method is called that has the log decorator on it. So now let's build the server app and run it. Now when we add a food item in our web app, it logs that insert update was called with these arguments and had this return value. We can now easily use our log decorator wherever we want to log when a method is called. In this video, we have looked at using decorators to easily extend the functionality of our application. This is a very exciting and cool feature that I hope you'll start using more often in your own applications. In the next video, we're going to look at how we can add parameters to our decorators. Hello and welcome to the last video in section 7 on advanced ES6 and ES7 features. In the previous video, we looked at implementing a simple log decorator. In this video, we'll expand on that example and use parameters with the decorator. We'll look at how we can add a parameter to the log decorator. Then we'll look at where we can find more information on decorators. Our log decorator currently only uses whatever logger main factory passes to it in the getLogger method. But what if we wanted to change it to allow logging with a specific logger class? For this video, we're going to change the log decorator to accept a parameter so we can tell it what logger class to use. To change a decorator to accept parameters, we need to create a function that returns the function we previously created. Let's go ahead and do that now. At this point, we have to add a logger parameter to allow passing in a logger to the decorator. And now we just have to change the inside of the decorator to use our logger parameter. Good. We're done, and now when we use this log decorator, we can specify whatever logger we want to use with it. For example, we could pass in mainFactory.getFileLogger. In this case, passing in a parameter each time is annoying, and so in the actual application, I've created a file logger decorator, console log decorator, and then a base log decorator that contains the common code shared between all these decorators. Here's the source code for file log, and you can see that it passes a file logger into base log for us, so that we don't have to do this manually each time. There's obviously a lot of information about decorators that we haven't covered in this section. Because of that, I would recommend looking at more information about implementing TypeScript decorators. This Stack Overflow question covers the essentials of how to implement class, property, parameter, accessor, and method decorators. Additionally, it goes into detail about how decorators work that's beyond the scope of this course. In addition to this, I would recommend searching online and looking into the Metadata Reflection API. The Metadata Reflection API enables you to emit serialized type metadata at compile time. The Metadata Reflection API enables you to emit serialized type metadata at compile time, and then use this information at runtime. It can be very useful in certain situations, but it's still currently in an early stage of development. In this section, we have looked into using some advanced ES6 and ES7 features. We looked at how generators work, improving the performance and efficiency of our application by using generators, writing easier to work with asynchronous code with async and await, an introduction to using decorators, and then this last video on providing parameters to a decorator. In the next section, we're going to look at bridging statically typed gaps. Hello and welcome to the last section of Mastering TypeScript. The previous section was on advanced ES6 and ES7 features. In this section, we'll look at several ways we can overcome statically typed gaps. What exactly do I mean by that, though? By bringing us static typing, TypeScript brought us out of the Wild West of client and server-side scripting in JavaScript. There's more ways we can benefit, though. What's shown in red is areas of an application that typically aren't connected with static typing. We typically don't have static typing between our server and client-side code, so if our server-side code for receiving requests changes, the client-side code that sends those requests won't throw a compiler to remind us to update our client-side code. Also, typically in our view code, like HTML, we haven't had breaking changes in the view code desirably notify us with compile errors that our client-side TypeScript is incorrect and needs to be fixed. We also haven't had compile errors when we use the view code incorrectly. In this section, we're going to look at ways we can solve all these problems with TypeScript. First, in this video, we'll look at a crucial element to bridging the server-client statically typed gap, which is sharing code across applications. Second, we'll look at a video on using interfaces and shared code to bridge statically typed gaps. For the example, we'll bridge the code between a client-server application with this technique. Third, we'll talk about a more experimental method of using code generation on the server side to update the client side. Finally, we'll look briefly at how using TSX files can help us bring our view code into statically typed TypeScript code. Now we begin our first video on how we can share code across applications. There's lots of ways of doing what we're going to talk about in this video, and so we're just going to do an overview of some of the basic principles. We'll talk about storing our code in one application and then pushing or pulling the code to or from the other application. Additionally, we'll look at storing the code separately and pushing or pulling the code to or from our applications. We'll also look at what's done in the Slice of Pizza sample application. In our Slice of Pizza sample application, we have our server app and web app. Sometimes we want to share code such as utility classes or interfaces between these two applications, or even other applications we work with. There's two main solutions we can use. The first is to move the code outside our applications, then either push the code from this area into our applications, or pull it into the applications from one of the applications individually. So for example, the server app might use a build script to copy the files from where the code is stored separately into the server app, instead of the code stored separately copying it into our server app. The second option is that we could store the code in one of our applications, then create a script that will copy it to the other. For example, the server app in this example contains the shared code and it's copying it over to the web app. This could also push the code to the web app, or the web app could pull the code from the server app. So which one of these methods should we use? Well, it depends. When you pick what to do, you should choose what makes sense for your scenario. In the case of our sample application, I'm storing our server model interfaces in the sample app, then pushing the changes made to the server interfaces to the client side in the server app's build script. The reason I'm pushing the changes from the server app is because it's an easier setup to ensure the web app has the correct interfaces. So what about pulling changes? Well, pulling changes is great for when we have reusable code to use in multiple applications, because it allows us to request code from the shared code only when we need it. For example, if we were to make a breaking change in our shared code, we would only be forced to change applications that request the new code. One of the best ways of doing this is to create a package. You can do that using npm or NuGet. I would recommend you research the topics shown here. For npm, a private npm repository allows you to privately keep and share packages across projects very easily. I would highly recommend it if you were to work with a team of programmers where you want to distribute the packages amongst your team. Another topic you could look into is using a local npm dependency. This allows you to specify a local file path that your package is stored at, then install it as a package of the current application. Finally, if you use NuGet, there's always the ability to create and install a NuGet package locally. In this video, we looked at sharing code across multiple applications. I would recommend you research and try out what was discussed in this video to find out what works well for you. You might even find better ways of doing this. In the next video, we're going to look at how we can bridge the server-client statically typed gap by using interfaces and a shared configuration. In the previous video, we looked at sharing code across multiple applications. In this video, we're going to look at how we can use what we learned in the previous video to help us create a statically typed bridge between our server and client application by using interfaces. First, we'll discuss the problem, then we'll look at a solution which uses interfaces and a shared configuration. Here's a very simple client-server application where both the client and server are programmed in TypeScript. Right now all it does is it will send a message to the server will display that message in the console, write it to a file, and then return back true to the client if the message is 5 characters in length, and false otherwise. You can see that here. A scenario that happens occasionally is a developer won't properly call the server from the client, or change something on the server that breaks something on the client side. So how can we reduce the chance of this problem happening and force everyone on our team to do things properly? First, the client needs to know the route configuration for making requests to the server. By that I mean the client needs to know what path on a server to send the requests to. For example, a put request to the message path. Second, the client needs to know the data that will be sent to the server. And finally, the client needs to know the data that will be received from the server. For this video, we're going to look at a diagram in order to describe the method of doing this. We won't step through the code itself. However, this example's code with the simple client-server application is available in the course's resources. So here we have a client application that calls some communication classes that contain code to send requests to the server. The server receives the requests and then passes that information to the server application. Now our first task is to store the route configuration in a central location so that it can be shared between the client and the server. We can do that by employing one of the methods we talked about in the previous video. So for example, we could store the route configuration in a TypeScript file in the server application, and then create a build script to copy the route configuration TypeScript code to our client application. Then we would use this route configuration when defining the code to send the requests, and the code to receive the requests. Since they're both reading from a centralized source, they'll always stay in sync as long as they properly use the configuration. Our next step would then be to make sure the data being sent from the client application to the server application matches. What we can do to help assist that is add another layer on the server side. We'll call these the server communication classes. Then we'll connect that layer together with the client communication classes by sharing an interface between each corresponding class and sharing interfaces for the data structures being passed around. For example, we could have a shared message communication contract interface that is implemented by a class in the client communication classes as well as a class in the server communication classes. This ensures that the types going through the client communication classes layer is the same as the types going through the server communication classes layer. In a sense, this connection with the interface is our strongly typed bridge. So in this case, the client application would call a method called sendMessage in the client communication classes that expects a message parameter that's a string, and it says that it will return a boolean asynchronously. Then the exact same thing will happen between the code that receives requests on the server and the server communication classes. So the server communication classes will expect a sendMessage method to be called that has one string parameter and will eventually return a boolean. Say we wanted to change sendMessage from instead sending a message string to instead send a title and a body string. Well, after our interface was changed, both our server and client communication implementations would error. Then we would have to fix our server class implementation to handle this change. But now after fixing that, we would get a compile error in our code to handle receiving requests. So we would have to fix that code too. Now we have to fix our client communication classes. But then by changing their structure, we would get an error in calling our code that sends the request. So we'll be forced to fix that too. So in this you can see we're making a change in one centralized location, and then we're being notified by compile errors about where in the code we're supposed to change next to make this work. One problem with this method is the code to send and receive requests could still have problems. However, we can reduce the chance of problems by using as much reusable code as possible. In this video, we have looked at one way of bridging the client-server statically typed gap by using an interface and centralized configuration. In small applications, it might not be worth the effort to implement this solution. However, in larger applications, this can make a bigger difference to help enforce that the client calls the server correctly. In the next video, we're going to look at a more experimental way of doing this by using code generation. In the previous video, we looked at how we can use interfaces and a centralized shared configuration to help keep a client and server application synchronized. In this video, we're going to look at a more experimental way of doing this by using code generation. We'll look at the overall method of doing this at a high level. Then we'll talk about where you can find an example of code that does this. Currently, at the time of writing this, there's not a lot of good tools for doing code generation, and so I've labeled this as an experimental technique. Overall, this video is more for fun, and I'll show you something new that you might not have known was possible to do with TypeScript. What we're going to discuss might open you up to more ideas about what you can do with TypeScript, and come up with better solutions to completely different problems. As in our last video, we have a client and server application, and we'll want to create a tighter link between these two. In this case, we'll start by writing our server communication classes. These will handle any client requests that come to the server. Next, in a build task, we'll use the TypeScript compiler API to analyze the structure of our actual TypeScript source code. The TypeScript compiler API can be extremely useful in situations like this. Then, using what we learned about the structure of the server communication classes, we'll generate the client communication classes with their dependencies. Then adjust the output based on any additional configuration we provided. After we share this generated code with the application or applications that call the server using one of the techniques we discussed in the first video of this section. In this case, we're writing it directly to the client application from the server application. At this point, we could access the auto-generated client communication classes from the client app, and now we have an extremely strong link between our client application and server application. So why is this technique good? Well, in addition to having static typing between our client and server, we also have a lot less code to maintain. We don't have to write the client code to call our server. We can leave that up to the code generator to do it for us, and it will probably do a more consistently correct job too. Additionally, this information gives our client applications accurate information about how to call the server. That makes programming and working with this much faster and easier. Talking to the server is as simple as calling a method on a class that's already defined for us. An example of doing code generation can be found in the sample app. However, remember that the way of doing this is still very experimental and might have changed at the time you are watching this video. It's for this reason that I would recommend, in addition to taking a look at the sample app, that you look up this method online to see if there are better solutions. In this video, we have looked at how we can bridge the client-server type gap by using code generation. I would recommend you check out the TypeScript compiler API in addition to all of this. You might think of other non-related useful ways to use it. In the next video, we're going to look at how we can use TSX files to bring our view logic into our TypeScript code in order to have static typing between our view and client-side scripts. In the previous video, we looked at bridging the server-client statically typed gap by using code generation. In this video, we're going to look briefly at how we can use TSX files to move our view logic into our TypeScript code. We'll look at what JSX and TSX files are, then at some additional resources on this subject. There's another specification built on top of the JavaScript language, and it's called JSX. JSX is an extension of JavaScript that brings XML-like syntax to the language. Similarly to TypeScript, it needs to be transpiled to JavaScript. A note about JSX files is that they are primarily used in the JavaScript library React. So now what is TSX? You probably guessed it yourself. TSX is TypeScript JSX. It brings what is done in JSX files to TypeScript in TSX files. Here's an example of a TSX file. In it, we have stored our view logic in a myDiv variable. You can see we're using XML-like syntax here to represent our view code. This would transpile to regular JavaScript code that represents what's being shown here. So what are the benefits of doing this? Well, we have static typing when writing our view code, and we have static typing between our view code and other client-side TypeScript code. To demonstrate this, the disabled property on the div expects a Boolean, and so if we were to change this variable to instead be a string, we'll get a compile error because disabled expects a Boolean. Or if we misspell a variable name, we also get a compile error, telling us that the variable we referenced doesn't exist. Additionally, we can get code completion within our view code. You can see here that when I go to add a property on div, it gives me a list of options to choose from. Had we stored this view information in HTML files instead of TSX files, we would not get these benefits of static typing. We'd only know if we had made a mistake at runtime. Talking about JSX and TSX files is a very large topic, and there's a lot more you can do with it that I haven't shown here. If you find this interesting, I would recommend checking out the React JavaScript library from Facebook. It's the most mature library that you can use with TSX files right now. If you find React interesting, then I would also recommend looking into Flux. Flux is an application architecture pattern that works well with React. I would highly suggest you check it out. Overall, you can see an example of both React and Flux being used in the web app in the Slice It Pizza sample application. In this section, we looked at how we can bridge statically typed gaps. In the first video, we looked at how we can share code across applications. Then we looked at two ways of bridging the server-client statically typed gap. One way used interfaces and a shared configuration. The other way used code generation for the client. Finally, in this video, we looked at how TSX files can help us bring our view code into statically typed TypeScript code. In this course, we have looked at many topics surrounding the TypeScript language. In deploying the type system, we looked at common troubles and misunderstandings some developers have when using the type system. We also looked at solutions to these problems. In moving to ES6 classes, we looked at improving our JavaScript code with ES6 classes. In interacting with the type system, we expanded on the knowledge from deploying the type system and looked at different language features that TypeScript offers us that interact with the type system. In representing JavaScript libraries, we looked at using and working with TypeScript definition files. In language features for code improvement, we looked at some useful language features TypeScript offers that weren't found in other sections. In advanced ES6 and ES7 features, we examined several features coming to JavaScript in the future that are available in TypeScript today. Then finally in this section, we looked at bridging statically typed gaps. Overall, I hope you learned a lot in this course, and that you'll use what you learned to write better TypeScript code. Remember though, that TypeScript is a rapidly developing language. There's a new version every few months, so make sure to subscribe to TypeScript's blog to stay on top of everything. Also, if you have any questions about the language, a good place to ask them is on Stack Overflow, tagged with the TypeScript tag. Additionally, an excellent resource on the language is the TypeScript Handbook. When you have to remember something on the language, it's a good resource. And finally, if you have any questions about this course, you can email me at dsherritt@gmail.com. So that's it. I hope you enjoyed the course. Thanks, and all the best.